Good morning, everybody. Okay, is the recording started?
Yes, fine.
Okay, fine. So we have Professor Anirudh Kulkarni with us today. So he will be delivering a lecture on porous media modeling using OpenFOAM. So let us all welcome Professor Anirudh to this faculty development program. So we have faculty members in a majority here, but we also have students here who have applied, and we have allowed them. And some of them are fellowship, the summer fellowship students are there, and the learning program students are also here.
Okay.
So I welcome everybody to this program. Let me just briefly introduce Professor Anirudh to all of you, and then we can go ahead. So Professor Anirudh Kulkarni is an assistant professor at PDEU, which is Pandit Dindayal Energy University, where he has served since 2020. He completed his BE in mechanical engineering from WIT Solapur, and followed by a PhD degree from IIT Indore in 2020. His current research focuses on development of CUDA accelerated LBM and IBM solvers for various engineering applications. He has published over 25 articles in reputed SCI indexed journals and is currently supervising 4 PhD scholars. Additionally, he manages 4 active research projects with a total funding of rupees 80 lakh and executes multiple consultancy projects for the industry partners. Here was a brief intro of Professor Anirudh Kulkarni. I hope you'll all find his lecture to be informative. And after the lecture, we will also have a interactive Q&A session wherein you can ask him the questions that will come up during the lecture. So over to you, sir.
Thank you.
You can
Thank
start
you.
the lecture session.
I hope I am audible.
Yes, you're audible and you're visible also.
Thank you. Thank you. I'll then share my screen.
Sure.
Yeah. Yeah, I guess the screen is visible. Can if someone just okay then. Let's move ahead. Yeah, thank you. So first of all, at the outset, I would like to thank the FOSSEE team for giving me this opportunity to interact with you on porous media modeling in OpenFOAM. Dr. Payal ma'am has actually introduced me quite well. I appreciate that. I thank her for that. So this and at the outset, I assume that you have a basic understanding of OpenFOAM and you're a novice to the field of porous media. With these two assumptions, I'll deliver this 1 hour talk. If you are an advanced user of OpenFOAM or you are aware of porous media, probably this interaction may not be that helpful to you because I'll not be adding much value. I'll be focusing only on the basics. So I hope that is okay. And with that assumption, I move on. So I will be focusing, as I said, on the physics, the equations, and how to implement both of these in OpenFOAM. All right. And what I'll not be doing is no code editing throughout the talk because obviously we have a very short duration over here. So we'll just focus on the physics, how to implement that physics through the equations in OpenFOAM. That is what we'll try to focus here. All right. So first, we'll focus on what is porous medium, and then what is the Darcy-Brinkman-Forchheimer model, how to do the solver modification, what case modifications are required, and then we'll run, or I'll show you the results that I've run. And 3 things that we'll be focusing on would be the model input, the solver input, and the output. So that way, we will get a holistic understanding of how to implement porous medium model in OpenFOAM. So if we focus on the governing equation, currently we are looking at the at a very general incompressible implementation of Navier-Stokes equation. Now, if we talk about the porous medium as such, then please try to understand the porous medium is going to be modeled as a resistance to the field. Now, to model this resistance, we need to add some source terms. And through those source terms, we will realize the porous medium in the field. There are various ways to do it. There are various models that are available, but the most applied, the widely famous or widely used model is the extended Darcy-Brinkmann-Forchheimer model, which is currently shown here. So when we talk about the resistance, as I said, porous medium resistance, so this resistance may, enforce itself as a viscous resistance and as an inertial resistance. So the viscous resistance, meaning when the fluid flow is at a relatively lower velocity, so whatever viscosity hinders the motion of the fluid, again due to the presence of porous medium, to realize that, we add two or one source term, which is the Darcy source term. So this Darcy source term therefore includes the effect of viscosities. So we have mu by k into the velocity, obviously assuming the rho is there on that side, or else it will be nu. So this k over here is permeability. This permeability term, as it suggests, right? It shows that how easily the fluid can enter the porous medium. So if the fluid can easily enter into the porous medium, the said medium will be declared as permeable, or else it will be said as impermeable. And what assumption does this model make, this Darcy-Brinkmann model? That this porous medium is a packed bed of spheres. That is what assumption, that assumption is what this entire model is based on, that it is a packed bed of sphere. So if I say that the fluid is entering this medium and it is not able to pass through, it is an impermeable case, meaning the Darcy term is, the Darcy number, or let me focus on first permeability, K is very, very low. So if K is very low, that means the medium is impermeable, the fluid doesn't flow through the medium, right? And that is what the permeability is all about. Now, when we increase the fluid flow, obviously the viscous effects become less dominant and inertial forces become more dominant. So in that case, we'll have to take that resistance into account, the inertial resistance. Hence, this particular term was then introduced, the Forchheimer term, which has CF upon root K, all right, and mod of velocity into velocity. Let me close the chat. It's a little distracting. Yeah. So as I was saying, right. So for the Forchheimer term, we have CF upon root K, mod of velocity into velocity. Now, this mod of velocity into velocity is what, the second order term is what is, taking into account the inertial resistance, meaning when we increase the Reynolds number, or when we increase the velocity of the flow, to incorporate the inertial resistance, this term was then introduced. Uh, Henry Darcy is credited to this inclusion of this Darcy term, and he established or declared this particular model in 1856. And later on, whatever developments have happened in this field. This Brinkmann term is very interesting. Now, in the Navier-Stokes equation, the diffusion or the advection term that we have on the right hand side, whatever how you perceive it. So if you let us focus on diffusion. So if we talk about the diffusion term, so in this case, if we incorporate the velocity as a local average velocity, then this becomes the third term, that is the Brinkmann term of this Darcy-Brinkmann-Forchheimer model. And you must be noticing, I have also included the epsilon term everywhere. This epsilon term indicates porosity. Now, what does that mean? So permeability tells how easily the fluid can enter the porous medium, and porosity tells me how many pores are there inside that medium. So these pores over here, these gaps over here, these gaps are indicated by the porosity. So I will talk about it. So this when we include in the velocity, because when the fluid is going to enter the porous medium, its velocity is going to change in comparison to the macroscopic velocity that is out there. So to incorporate that, we'll have to take or multiply the porosity term, and hence or include the porosity term, and hence we get to see this epsilon term everywhere in the equation. Moving on. So the first part, let us talk about the physics, which I've briefly talked about, but let us talk a little bit more about it. Now, see, I've told you that the Darcy-Brinkman-Forchheimer model assumes a packed bed of sphere. Now, at what resolution level do you realize this pores is what will govern, or this will govern what model you end up choosing. So, if suppose you want a pore resolved case, meaning a microscopic case where you focus on the pores and the fluid flow around these pores, then you will model them as spheres and then study the fluid flow around them at a microscopic level. So obviously the physics there is going to be entirely different. But if suppose you zoom out and you average it for a certain continuum, then we have a macroscopic model at hand, and this averaged velocity, in that case is not going to be the pore scale velocity, right? That is sampled at any point. So we'll have to do a certain averaging exercise, which is known as the representative elemental volume. There's a very good book by Professor Arun Narasimhan. When I was starting out in this field, I had read that book. You would also, if you are very interested in entering into porous medium, you should read the book by Professor Arun Narasimhan from IIT Madras. In that, he has talked about all these things, and these are very basic aspects. I'll not go there and confuse you, but for now, understand that when we are talking about a continuum, we'll have to do a certain averaging so that we realize the porous medium properly, and this continuum model will be valid only to the extent that the closure parameters represent the unresolved geometry. So this is very important, and we have to take this into account before we move ahead. Now, if we resolve the pores, obviously we'll get the actual solid fluid geometry, and no slip we can model on each grain and wall. But obviously in that case, the mesh will be very expensive, and obviously the time step accordingly will reduce, and it will be very heavy on your computational setup. And because of that, you'll get a good local detail, but the scale economy, device scale economy will be very poor. Hence, if suppose pore resolved geometry is not required, we tend to use this macroscopic porous continuum model. That is the extended Darcy-Brinkman-Forchheimer model, where we can get cell-wise porosity, permeability, and Forchheimer term. And then the representative resistance can be modeled through source terms. So you don't have to then resolve at the pore scale. You can just add two source terms and take the average velocity into account, and voila, you have a porous medium modeling at hand. And it can be feasible at any device scale. And obviously, through experimental validation, it has been proven that it is fairly accurate. So that way, you do not have to create any microstructural truth over here. It can give you a fair macroscopic approximation without having to go down to the pore level geometry. So let us talk about a few basic terms. Porosity. So as I have told you, porosity indicates that what is the void that is there in the porous medium, how much more void is present in that medium. And to calculate that, what we can simply do is we can calculate the volume of fluid to the total volume of that medium. And this non-dimensional number between 0 to 1 will give us how much fluid or void is present in that medium. So if suppose epsilon is 1, that means it's a clear fluid region. There are no pores to look at. And if it is falling into a number anywhere below 0, obviously that means there are some pores in that region. So that means we are looking at a porous medium. So for instance, if we have 0.6, that means in that region, in that area, the porous medium domain, we are looking at 40% fluid volume, and the rest is solid area. That is what we can say. So As I said, 0 to 1, this non-dimensional number lies, and it is a very important parameter when we talk about realizing the macroscopic domain or a macroscopic flow. Now, obviously, uh, on a side note, if suppose you are modeling flow across a square cylinder, in this case, you are more interested in understanding what happens behind the this porous square cylinder when the fluid flows around it. So there, probably by changing porosity, the physics may hardly change. However, if suppose you are modeling an internal flow, when there is a porous heat exchanger, and there you are wanting to study how this porosity increases or decreases the heat transfer rate. So in there, obviously, porosity variation is going to make a lot of difference. Now, what happens is a lot of papers, because see, as I've told you, the model is really simple. By adding just two source terms, you can realize the porous medium, and you can get going with it. So people publish papers like crazy in this area. You go and search porous keyword in the titles, you will find hundreds of paper that get published every year, and mostly around 90 to 95% of them are incorrect, and I'll tell you how. So first thing is that and in OpenFOAM, as you have seen, the default solver, obviously, as you will see in your practice session, does not take it into does not take into account this porosity term. So like that, there are a lot of things that need to be thought about as a person who is just entering into this field. So porosity is one term in that. If suppose porosity variation does not cause any change in your domain, it's fine, but you will have to include it and prove that. You cannot blindly ignore it, even for external flow cases. So one has to be very careful about that. Now, we'll talk about how to implement this in OpenFOAM, but let's move on. Now, the other term is the Darcy number. Now, the permeability that we have talked about, the K, as I've told, it gives you a fair, understanding of how well the medium is, uh, how can I say, conducive for the fluid flow, meaning it is how easily it is allowing the fluid to enter the medium. So if you look at the unit of permeability, it's meter square. But again, for the cases of non-dimensionalization, the non-dimensional reference number in this case would be the Darcy number, obviously credited to Henry Darcy, which I have already told you, right? Now, the Darcy number is written as K by H square or L ref square, meaning the characteristic length, and K will be the permeability. So obviously meter square, it gets non-dimensional, and Darcy number is the popular non-dimensional number to indicate whether the medium is permeable or not. So if Darcy number values are very less, that means it's an impermeable medium, and if Darcy number is more, that means it's a permeable medium. It's that simple. So again, if suppose we are modeling porous medium, we'll have to include this number in our simulations. Now the second part, the Darcy-Brinkman-Forchheimer equation. So let us talk about a little bit more about it. Now, obviously, if we look at the Navier-Stokes equation, various terms, I've already told about the various source terms, the resistance, right? The Darcy would be incorporating the viscous resistance, and the Forchheimer term would be incorporating the inertial resistance. And it's not like these two terms are the only two terms in this particular model, or this is the only way to realize a macroscopic porous medium. This is the most basic model in that field, right? You can look at it this way. So do not be fooled by the papers, research articles that this is the truth, but no, this is not the truth. So let us talk about a little bit more about LREF. Someone has asked in the chat. So this LREF, or say H, whatever you want to call it, is the characteristic length. For instance, if suppose we are studying flow across a porous square cylinder. Okay, so in this case, what should be the characteristic height? Obviously, the characteristic height of the cylinder. So that will be treated as characteristic length. Why? Because only in that region, only in this region, porous medium is present. So if suppose we have a cavity and the cavity completely is filled with porous medium, in that case, what would be the characteristic length? Obviously, the height of the cavity. Where, so basically, in whatever region the porous medium is present, the characteristic height of that region is the characteristic length. It is that simple. Now, so let us talk a little bit more about Darcy term and its open form implications. So as I've told you that the Darcy term talks about the yeah, obviously flow direction. It will depend on the flow direction. So yeah, moving on. The Darcy term. So the Darcy term, it talks about the viscous resistance. I've already told you this new obviously indicates the presence of viscous resistance. We have K in the denominator, and obviously if we non-dimensionalize the equation, so instead of K, Darcy number will come here. And what is Darcy number? K by h square. So obviously K will be Darcy number into h square. So that way you would incorporate that here. Now, what is the effect of adding this source term? Simply that we get a linear velocity damping, meaning reducing K increases the resistance sharply because it is in the denominator. Now, how do you deal with this in open form? You simply create a source term, right? Through by using obviously FVM. So that way you can incorporate the Darcy term. And if suppose you want to have a clear region even after including this source term, just increase the value to a crazy high value of the Darcy number. So that way the Darcy number will be very high, meaning the fluid will be almost clear. So you don't have to go for 10 to 20 and all. Yes, 20 to 4 or 5 even should do the trick. What about the Forsheimer term? Again, Forsheimer term, inertial resistance. CF is the Forsheimer coefficient. It's calculated 1.75 divided by under root 150 epsilon cube. This epsilon is porosity. So this is how you calculate CF, and you substitute that here, divided by square root K and mod of velocity into velocity, obviously, as I said, for the non-linear inertial resistance. And this is a very important line which I've added here, is that it becomes important when local velocities through the porous region are not small. And this is when I mean what I mean by higher velocity. So inside the porous region, when the local velocities they exceed a certain range, we should realize the Forsheimer term. Now, what is that range? That depends on the case to case basis. So whenever as even a novice, you are starting out in this field and you are running simulations, you should always run the simulations by using the extended Darcy-Brinkman Forsheimer model, and then remove the Forsheimer term and compare the results. When the results don't change, only then only the Darcy term is sufficient. But at the outset, just by looking at the case and saying that the velocity is very less, I'll not take the Forsheimer term into account, that would be rather very immature to do that. So we should first include all the terms, run the simulations, and compare the results without those terms, and only then can we declare that only the Darcy term or not including the Forsheimer term would be the wise choice to do so, right? Obviously, it's a non-linear term, so we'll have to do some linearization. Now it depends on you how you want to linearize it. This is one of the various methods to do it, and as a novice, that's the reason why I kept this very simple. This obviously is not the most practical way to do it, but for a teaching purpose, yes, or learning purpose, yes. Moving on, the Brinkman diffusion. Now, obviously, as I've already told you, the diffusion term is already there. The only thing is that how this becomes the Brinkman term is when you include, when you include the local velocity into the play. If you don't do it, if you don't, how I can say this, consider the local velocity, meaning include the porosity term, then you are just playing around with the Darcy-Forsheimer model, and you are heading towards a very wrong result. Again, I caution you when you go and read research articles, a lot of them don't include this. But as I have told you, you have to include the whole model, then remove those terms by comparing the results before and after, and only then you should make these tampering or these changes with the model. So please be very careful on that particular front. Okay, so if we look at the source term all put together, how that would look in open form. So first things first is I'll define a coefficient, the effective porosity, and I will, you know, take whatever is the maximum value based on, this particular source term. I'll define the permeability K, I'll define the porous coefficient. Obviously, if suppose you are very, very new to open form, this might look very strange to you, but just look at the formula and look at the code. They are very easy and simple to understand. The beauty of OpenFOAM is that the language is very user friendly. So even if you don't have, deep coding knowledge of C++, you are still, you can float through and understand at least the basics of it. So that way, I will encourage you to look into this. Look at the formula, look at the code. It is very fairly simple to understand. I've just implemented what is there given here in this particular code snippet. So it's not that challenging to understand. So I've just assembled the coefficients. Now, if we look at the finite volume matrix, so the only new matrix contribution here, if you actually think about it, is this, right? So this is obviously going to be a diagonal source. It damps the velocity without any custom sparse matrix assembly requirement. So that is the beauty of it. Now let us look at the third part, the OpenFOAM solver modification. I choose icofoam, and I was just discussing with Evan that we should talk about the code modification and solver modification. So he will share the case with you. If time permits, he may talk about it because he has some plans related to other cases. But yes, even that is based on this particular philosophy. So I don't think I'm going to be talking about something new or something altogether different here. But yes, do explore the Google Drive. He has uploaded the zip file there. So I've uploaded both before and after solvers and before and after cases, so you can run them for your understanding and learning. So let us talk about the OpenFOAM object map. Now in the input output field, what changes do we need to make? Obviously, as I said, this and this are the new terms that I need to include, right? And on the basis of that, I'll have to calculate the derived fields. This will obviously go to the momentum matrix U equation. They will then go to the pressure correction and vice versa. I mean, again, this loop will continue thereafter. So if you look at the latest 2412 version, the pressure correction sequence must include a constraint H by A, adjust phi, and constraint pressure. If you are new to OpenFOAM, probably these things may sound a little strange. You can look it up. The entire manual is there online. It's not difficult to understand. So, but the only caution that I would like to point to you towards is that if you're doing these code modifications, omitting this, may cause some kind of closed cavity continuity failure, which I faced while modifying the code. I was doing that from novice perspective, so just be aware of that. Now, let us talk about the before and after solver. What is different? So if we look at the pressure and velocity fields in the regular icofoam solver, and say I modify the solver to porous dBF icofoam, same, nothing changes. Obviously, these epsilon Darcy number and rather the porosity Darcy number and porous number coefficient, they were not there. Now they are here. In this case, in icofoam we have a piezo algorithm. So accordingly, you'll have to take care into account. But that pressure correction algorithm, in that you don't have to do any as such heavy modifications. The code is there with Evan. He will share it in Google Drive, so you can have a look. The permeability is not there in icofoam, so we'll have to add that. How do we add that? Very simple, dA into h square. That is how we do it. And in OpenFOAM, or rather porous dBF icofoam, how do we incorporate this epsilon, d, and cf through wall scalar fields? Because these are scalar terms. They are constant terms. You don't have to go, they are constant values. You don't have to create any vector fields for that. No such headache. Now, momentum sink obviously is absent here. Here we do have to add. Remember, in a couple of slides before, I've shown how to incorporate this. Advection flux, if we talk about the icofoam, we have only phi. Here, however, we'll have to divide the porosity by it. Remember, we talked about taking into account the local average velocity. In pressure equation, obviously there is clear fluid correction, nothing happens as such. But here we'll have to, the correction should be weighted by epsilon into RAU, and that is very important. So what is epsilon here? Porosity. Please note this particular part. Now, moving on. So if we talk about the solver inclusion and setup, uh, if you look at this case, no dramatic changes as such, right? Here in the transport properties, again, I have not touched anything as such. However, here comes the part that along with the definition of kinematic viscosity, I will define the characteristic length, and I'll also define the K-min, the porosity floor. That these things are going to be required in the source sum linearization that we earlier talked about. Then we have porosity, we have Darcy number, we have Forchheimer coefficient. So I'll simply define scalar fields by using any how can I say, any standard solver. So if suppose you are very confused about how to make these changes, this looks very confusing. Term by term, if you look at it, it's very simple. So what I'm doing is I'm defining a volumetric scalar field with the name porosity, and in the input output object, I want the OpenFOAM solver to look for porosity, name, and obviously, so as the simulation runs during the runtime, I would want some changes to be made here. I would want the mesh to be updated accordingly. So it should be read. It should be read. And if suppose any changes are to be written, it should be written auto write, right? So these terms that way, as I've told you, are very simple. And obviously, once all this is done, mesh again has to be updated. So what I'm trying to say is all these things are very simple to understand. The terms are very simple to understand. And if suppose this format is very new to you, you can simply go ahead and copy it from some online GitHub repo, or even from the OpenFOAM installation that you have. You go and search for some other solvers, you'll find this template. You can just copy paste here and edit it. As a new OpenFOAM user, that is what I did back then. So I hope that should work out. Now, then there is a volumetric scalar field porosity effect. Obviously, this I require for the normalization. Then we have the permeability, again the porous coef. So that particular porous coef here, for that, I have a simple formula which I talked about, nu by k, and the inertial, the Forchheimer source term, the inertial source term rather. Sorry. So that is what we do here. Once we have defined all these things, so in the runtime, in the main loop, I will calculate the effective porosity. Then I will update permeability k, and accordingly I will update the porosity coef. This is what we'll keep on doing in the main loop after doing the essential prep work before the main loop, which I have shown just now. So this Forchheimer coefficient, obviously, it depends on the mode of velocity. So it must be refreshed as the flow evolves. And this is a very important point to note as a new user. Now, this is another thing, meaning the porosity weighted average advective flux. Sorry, the porosity weighted advective flux. This we have to do when we take into account the local average velocity. So phi by porosity is what a surface scalar field that I create, and I simply phi divided by FVC interpolate the porosity effective porosity term. Now this is purely a teaching implementation, right? It is not a general multi-phase or a compressible porous media solver. Please note that particular point. Again, as I said, I had declared in the beginning that I assume that you are new to this field. So this important point has to be taken into account. As I've already told you, there are tons of papers who blindly go ahead and use this macroscopic model even for a multi-phase or a compressible case. That should not be done, because the treatment or the models, they change depending on the physics. So for an incompressible case, for a very simple case, this implementation will work. However, if you're going for a compressible or a multi-phase or some complex problem where multi-physics is there, then in that case you should treat this term differently. I hope this particular point is noted. Now in the momentum equation, obviously the time term is there. After that, I'll modify the convection term accordingly, the then the diffusion term or the Laplacian term, and then we have the source term. And once we do that, on the right hand side, right, I will add this particular term so that this effect of local average velocity is complete. And one thing that I would want you to note is that the sign here is correct. So since it is on the left hand side, corresponds to the negative resistance. So we on the right hand side have kept the sign. So the sign is correct, nothing doing there. So if you do this modification along with this modification for pressure correction, you are good to go. So that way, your entire solver is now complete. And after tying them together, I'm just skipping through the code part. You are good to go. So in the obviously files and options, you'll make whatever changes you want to make for the custom solver. And let us talk about the case now. So for the case, I've chosen a very simple case. In a lid-driven cavity, let us add a porous obstacle. Again, if suppose you directly jump into flow across a porous square cylinder, probably that may be a little overwhelming in the block mesh case. Hence, I thought that this is a very simple case to understand, that we have a lid-driven cavity. Lid-driven cavity case is already there in OpenFOAM. So just you'll have to copy that and you'll have to modify a little bit. And what modifications needs to be done? Let us talk about it. So in the lid-driven cavity case, what we do is add a simple porous obstacle, simple porous square cylinder in the center, right? And we can add it in the center and keep everything else same, meaning the boundary conditions are going to be same. Nothing, no modifications need to be done there, right? So block mesh obviously remains same. As I said, the boundary conditions as well, nothing needs to be done there. Okay, initialization. So the porosity field needs to be initialized. How do you realize the porous medium? Now that becomes, or that is the question here. Obviously, there are multiple ways to do this. You can use FE options, you can use topo set, set fields, right? So what I suggest is that you once have a look at the case that I've shared, and that way you will be able to understand a simple approach to do this. So what I do is, in the entire field, first I declare clear fluid, meaning I do not declare anywhere that there is any modification or presence of porous medium. First I declare that the entire field is clear. So that will be my default values. Then what I do is I use the box to cell approach, and I define in a certain region that the porosity is different, the Darcy number is different, and the Fossheimer coefficient is different, meaning in the entire field, the entire field is clear, but there is only a certain region where these values are going to be different. Okay. Now, here is another important point. As a new user, or as someone who is just entering into this field, this is okay. For understanding the implementation of porous medium, this is okay. You are forgiven. However, if you go ahead and publish this, this is a mistake, because you will have to realize that if we talk about the porous medium interface, suppose this is the porous region and the fluid is entering into it. Now try to understand, earlier the fluid did not have any resistance to it. Now suddenly it is facing some resistance. So there is change in energy levels. Hence, at the interface, we will have to treat the fluids the fluid entrance into the porous region separately or differently, meaning we will have to take into account some interface models as well. And again, the research articles, almost 90% of them that have been published in this field assume a continuity model, meaning they do not use any sort of interface model. which may lead to wrong results. And I'll tell you a very interesting case study that is there right now, available in this field. So, uh, if suppose there is a domain inside, I keep a very blunt porous object, meaning say porous square cylinder. So it's a blunt shape. And suppose the Darcy number I change between 10 raised to minus 6 and 10 raised to minus 2. Now 10 raised to minus 6, remember, is going to be an impermeable case, and 10 raised to minus 2 is going to be a through flow, meaning almost no resistance to the flow, right? So that, what does that mean? At 10 raised to 6, when the fluid comes, it hits the cylinder, moves across it. In 10 raised to minus 2, the fluid comes, it hits the cylinder, passes right through it. So these are the extreme ranges. Now, obviously, as the general logic goes, if suppose I am plotting the coefficient of drag, say, or say coefficient of lift across this, for various cases, say 6, 4, 3, and 2, obviously minus 10 is minus 6, 10 is minus 4, 10 is minus 3, 10 is minus 2. If suppose I plot the coefficient of lift, as per your general logic, what do you think will be the trend of this curve? Just put something into the chat while I drink water. What should be the trend? Can someone in chat just tell me what should be the trend ideally? A straight line, a curve, linear downward? Yes. Uh, you know, Perfectly said by a person there that it should be downward linear, obviously. But surprise, surprise, in the literature, it says first, first the CL, it starts reducing, but then uh, there is a jump. Yeah. So at the intermediate permeability levels, there is a jump. Yeah, let it sink. So I was also surprised as a PhD student at IIT Indore when my thesis supervisor gave me this particular case to understand. I was also surprised, and the funny part is that there are no experimental works that prove this. There is only one paper by Notebook, and in that paper as well, the experimental part is not that clear. So the entire world has been using this without any questions. Why? Because obviously the universities and the research environment, how it works, that how research article publishing pressure is there. And if just by adding two terms I get a paper, I do that. I don't question things. So yeah, I mean, lately I'm studying a little bit more about this. What I have noticed is that in that external flow, if you apply a proper interface model, this jump goes away. This jump is unphysical. It should not be there. It's a numerical artifact at the max. And these things you get to learn when you spend some time in the field. But when you are just starting out, when you see people publishing papers like crazy by just adding two source terms, you feel that, okay, I can also do this. And not just Indian authors, many European and US authors as well blindly use this model and publish in JFM, Physics of Fluid. So I would, challenge them to prove this physicality. So hence, please take this with a pinch of salt, apply a proper interface model, and only then go ahead with this. But see, for that, you cannot do this code simplification. For that, you'll have to develop a custom library. It's too much work. If in OpenFOAM, already there's an option to add the model by using just say toposet, I do that. I go ahead, go home and sleep. I publish papers and get promoted. So my request to you, you are starting out, it's fine. You study the case, that is fine. But think about the interface part as well from a physics perspective. If you most of the faculties here are I assume they are faculties. They should think about this. That when the fluid enters the porous medium, there's a change in the medium. Hence, at the interface, there will be some kind of stress jump. So that aspect has to be taken into account, and a model has to be chosen appropriately. Again, this area has been completely unexplored. Very recently, not many papers have been there. Only in the couple of decades ago, there were some papers, but yeah. So you can also look into this particular aspect. I think I've talked a lot about it. Moving on. Now, in obviously constant transport properties, we make these changes because we have defined those terms before. And in schemes, obviously, we can choose simple second order schemes, nothing fancy here. Piezo, again, you can have a decent and corrector, all these values for starting. These values are fine. And you can then run and compare. So I have ran these cases for you, and this is what I got. So with and without is the comparison here. So without, obviously, lid driven cavity, we all know what happens. Obviously, I did not run it entirety. I ran only a couple of steps. So obviously, this will go. This center of vortex will move, and you will get to see a fully established flow. And if in this case I add a porous square cylinder somewhere here like this is what I get to see. So I've added a decent Darcy number, meaning the fluid will enter the medium, flow a little bit around, and come out of the porous region. Again, this case is available. You can explore during your hands-on exercise, right? Okay. Now, minimal sanity checks. Just keep this in mind. First, we'll have to have a very clear fluid. In that, we will add a porous resistance. So if suppose we want to check the Darcy dominance, we'll have to decrease the dA. Velocity inside the porous region should normally reduce. If we want to check the effect of force term, we'll increase the CF. If we want to look into the aspect of pressure reference, then the closed cavity needs at least one pressure reference cell. So that as well we'll have to take into account. Now, what I would expect that you study at least 3-4 cases in your hands-on session, so that you understand the effect of porous medium presence and how it changes the physics. Obviously, the porous medium has applications in real life. You are a porous medium, I am a porous medium. At some resolution level, we all are porous. Every aspect of this world is porous at some or the other resolution level. So you will find tons of application in heat transfer, fluid flow control, and passive heat transfer applications, etc. So you can explore that on your own. But for this particular tutorial session followed by this talk, I expect that you at least try a couple of cases so that you get the feel of it. Now, commonly what may happen is that in transport properties, you may use wrong dimensions. It used to happen to me, so I thought I should mention it. And in set fields, you may forget to turn on the porous solver. Maybe pressure outlet for closed cavity, you may incorporate it wrongly, or even you may use a very small DA without changing the time steps or something like that. Maybe some continuum model you may expect, and then try to achieve scale recirculation. These kind of things you may do at the beginning. So please be aware that these things would be bugging your results. So caution, trade cautiously. Then why FE options can we use? Right, FE options why can't we use FE options? FE options, yes, obviously we can use for production work. We can modify the source term in FE options directly. We can do that as well, which is already available in OpenFOAM. But I did this for the teaching purpose, so that you understand what's going on behind the curtain. And again, try to understand whatever solver I have given. This is only a pedagogical solver. It does not claim a general porous media platform. So do not go ahead and use it for your search purposes. It's just for teaching, learning purposes, pedagogical purposes. I guess this part will be taken care by Evan. And if we would want to then look at the important takeaways. So I have talked about the extended RC Princeton four chamber model. I've also talked about the Darcy Dragon four chamber direct terms. I've also talked about the effects of local porosity, and we have talked about the implementation, and obviously verification, demonstration, and validation benchmarking. You can go ahead and do it. And I have also cautioned you about the current research scenario and the various aspects of it, because I've spent a decade almost in this area, so I know a few things about this models. So I thought that I should let you know. But again, that book by Professor Anu Narasimhan, if you read that, probably it will take you 2 or 3 steps ahead in comparison to reading multiple research articles. Then there are obviously convection in porous media. That book by Neil Dan Bajan is there, Convection in Porous Media, by Neil Dan Bajan. You can read that as well. And then there is OpenFOAM Primer, a book called OpenFOAM Primer. You can read that. You will find some aspect of porous medium modifications or library modifications there for modifying the solver. And yeah, that should do it. That should do it. Yeah, that should do it. Okay. So I think this is a nice time to wrap up the session. If there are any questions, we can, if there are any queries, we can have that here now. Thanks for giving me your time. Thank you. Yeah. You can you can also read the book by Professor Kavyani. That's also a good read. I would like to conclude here. Payal ma'am.
So there was one question in the chat. It was
Yeah.
saying that for the porous term, we had a source term. Why not a sink term?
I don't understand the question.
Oh,
What is, I mean, in what context are you asking this sink and source?
So can I ask the question? The question
Yeah,
was
please.
mine.
Please go ahead. Please go ahead.
So when you are solving the governing equation, you have some term called source and sink at the end, right?
Okay.
So
Okay.
first few slides you have described that you are having the source term, but when you compared with the cavity case, you shown that it just kind of sink.
Okay.
So that I'm a bit confused. Like it's just like source term, adding source term is causing as a sink, or sink is causing as a source. So that's why I asked that question.
Okay. Can you give me some context in the sense that when you say sink term, what particular case or aspect that you are talking about?
So let us suppose if you have some heater. Let us suppose I have a heater, and
Okay.
that's passing through like permeable body. So that will act like a source, right? Heat source.
Okay.
Or maybe some. I'm not pro in this, so I haven't run this kind of porous. I run most like wave case with porous media, so I'm not sure how it's working.
Okay. Actually, I'm primarily speaking from the perspective of CFD, to be honest. And in CFD solvers, when we talk about source terms, we often talk about the linearized source terms to aid the convergence. So say for instance, I talk about say S phi is equal to say SU plus SP phi. So here obviously the SU part will be the explicit part, and the SU will be the, sorry, SP will be the implicit part. uh, right, SU will be the explicit part, and SP will be the implicit part. And for numerical stability we'll talk about this. But then when you talk about the source terms, the physics is where we are talking about the source terms. The convection and diffusion terms are standard. Okay, I mean, see, this sink and source, you are looking at it from a physics perspective. In CFD, we are talking about source terms is what the additional terms that you add to the governing equation. So these are two different things. I hope I'm able to clear your doubt there.
Okay, thank you.
Yeah. Anything else?
So there's one more question regarding your case, which
Right.
you showed. In that, what exactly is the Reynolds number?
I think it was 100, if I'm not wrong. I mean, that doesn't matter what was the Reynolds number. I think I had picked the OpenFOAM case, the lid-driven cavity case from the OpenFOAM solver itself. So I think it was 100, if I'm not wrong.
Okay, sir.
Yeah. You should initially try this at a lower Reynolds number, because at higher Reynolds number, the turbulence, suppose for instance 10,000. So the turbulent model has to be taken into account, and there this porous medium model will entirely be different, in the sense that you'll have to make heavy changes if you actually want to capture the macroscopic model there. So I would not suggest going crazy with the Reynolds number for now. Just keep it at somewhere 100, so that you can understand for lid-driven cavity case, so that you can understand the physics better.
And so there's one question on YouTube. So it is, can you explain how to model perforated object with porous media inside another perforated object, like a perforated or porous drum?
Biodisperse porous medium, is that they are talking about? Meaning, say there is so there is a perforated plate, and inside there is another perforated plate, something
Yes.
like this?
Yes.
Okay. Yeah, you can model this by creating multiple zones. So what you will do is you will create, say for instance, zone number 1 here and zone number 2 here, and you will assign different properties. Now, obviously, again, in this case, at the interface, you'll have to apply a certain, model. At least you'll have to minimum at least take it the account stretch jump. But yes, if you do this, you create multiple zones, you can assign the porous properties differently, and you can model this.
Okay, sir.
Macroscopically. Yeah, okay. Are we good here? Then can we conclude? Yeah, please go ahead. I mean, you can ask questions. I would be more than happy to interact. Yes.
My question is that you said that the porous medium means it offers the resistance to the fluid,
Okay.
and the source terms describe the that resistance. Am I right? In the model, like
Oh.
that.
Maybe. I mean, yeah. Can you repeat?
I said you said that porous. If there is a porous medium, it will offer some resistance to the fluid.
Correct.
To the fluid.
Correct.
Okay, and now to model that resistance,
Right.
we add three source terms.
No, not 3 source terms, 2 source terms. And the existing diffusion term, you'll have to modify by taking into account the local velocity. So these 3 changes you will have to make. Yes.
Those 3 changes required to model the resistance.
Yes.
Am I right?
Yes.
Okay. Thank you.
Yeah. The resistance, the Darcy resistance, the viscous resistance, the Forshammer, the inertial resistance for this, resistances, and the Brinkman term comes from the fact that you take into account the local averaging velocity. Holistically, actually, the Brinkman term came into account for the diffusion parameter in the advection term in that Gaon equation. So it all started from by Henry Darcy, this porous medium field, at least the Henry Darcy, he was actually a civil engineer. He was assigned to model, analyze the piping system or design the piping system in Dijon, France. And during that, he came across this particular thing that where the pipes were clogged by, basically the pipes were clogged, the water flow rate was different, and he said the experiment with the pipe and resistance in it, and he later realized that the pressure gradient, its behavior was changing with respect to the fluid flow, and that constant that came out of this relation was permeability. So that is how the effect of viscosity came. So the initial equation is not, if you look at the old research articles, when we talk about the Darcy regime, they used to model only the Ergun equation, not the whole Navier-Stokes equation. Only then later on, when higher fluid flow and better computing power came, so higher fluid flow was modeled. So there people started then applying this to a macroscopic Navier-Stokes equation model, and that is how this entire extended Darcy-Brickman-Forsheim model DBF has come into the picture. So yes, for realizing the porous medium, we need 3 modifications to the Navier-Stokes equation, adding 2 resistance terms, the inertial and viscous terms, and modifying the Brinkman term. At least these three modifications need to be made. Again, for porosity, there are 1,000 models for porosity itself. So for porosity, currently we took a constant value. But say, if we talk about, a medium, say for instance, if we talk about any medium like say sponge, when we come from core to the surface, the porosity, if we plot it, it is linear, meaning at the surface, the porosity is higher than the core. So this is called a channeling effect. So like that, for porosity itself, there are various models like linear porosity, variable porosity, random porosity, and I can go on and on. So there are thousands of models there for modeling just porosity term. So like that, this field is very vast and it has a lot of models in it, mathematical models. But when you're starting out, you can start out with a constant porosity model and then accordingly change the model. For that inertial term and viscous term also, the term that I have shown, the model that I have shown, they are the popularly used model for modeling these resistances. But again, there are various other models as well. Although all these models have been given in either Professor Kaviani's book or Neil Denbajan or Professor Narasimhan's book. So you can find those details there.
Can I ask one more question? Like in the last slide, you have talked about that you have used like piezo solver.
Sorry, which solver?
Piezo, pressure implicit. You are solving pressure implicitly. Yeah, this one. Piezo solver modification. Have you tried with like simple or pimple? Or it like all the giving the same results, or the result is depends sensitive to the solver?
Actually, the results, see, it depends on the physics that you are modeling. So the pressure correction algorithm you will choose based on that. What is pimple is a combination of piezo and simple. So that should not drastically change your output. You use that for the case-to-case basis. The physics that you are resolving. For that, you will choose the pressure correction algorithm. That does not change your results.
And for the time discretization, are you using like first order time discretization or second order time discretization?
In OpenFOAM, whatever model we have, we can currently stick to that. We don't have to, focus on that particular aspect as far as porous medium modeling is concerned. You don't have to worry about time discretization part for OpenFOAM, as long as this porous medium model is concerned.
I think so, because we are solving like second order governing equation. So if we discretize the time by like second order time discretization, that will be more perfect to solving the equations.
Again, it depends on the physics that you are resolving. But currently for porous medium modeling, we don't have to think too much about these things. Evan, shall we stop then?
Yes, sir.
Yeah, because I think we have run out of time. You also need to continue for your session.
Payal ma'am, are you there?
I'll stop presenting. I think Payal is not there. we can wrap it up if you are comfortable to do that.
Yes, sir.
Yeah.
Okay. Just share my screen.
Yes, I'm there.
Okay. She has come.
I was just typing on the YouTube. Somebody
Okay.
asked that attendance is given, so I was.
Okay.
Okay.
We missed you.
Yes. Okay, so a lot of appreciation for your talk, Professor Anirudh.
Thank you.
So I have taken the screenshot. I'll be sharing it with you. You can
I would
also see the
appreciate that.
live chat in the YouTube.
Yeah, actually, after a very long time, I'm talking about porous medium, to be very honest. It was the topic of my PhD thesis. I've done a couple of things back then in this area, and
Okay.
it was very nice talking about this topic after a long time. Yeah.
Yeah, okay. So thanks a lot
Thank you.
to you. And Professor Anirudh Kulkarni is one of our esteemed faculty partners, and he guides many of the interns and fellows of FOSSEE every year. And he's always there for these lecture sessions whenever we organize the workshop. And FOSSEE is really thankful to you, Professor Anirudh.
Thank you. I do appreciate it.
Yeah.
Okay.
Okay, so so participants, if you have any more questions for Professor Anirudh later on, if anything comes in your mind, you can just write to us at contact-cfd@fossee.in, and we will coordinate and get back to you with the answers. Okay, so we are winding up the lecture session here now, and we are moving ahead with the hands-on session. So from the FOSSEE team, we have Evan Fernandez who has joined. So Evan will take you through the hands-on session. So, thanks a lot, Professor Anirudh.
Thank you, and best of luck, Evan and Payal, for the upcoming sessions. Very nice. I mean, I will also looking at the reviews, and very nice reviews for the earlier sessions as well. Great job, always, and I wish the best for the FOSSEE team. Thank you.
Yeah,
have a great day.
For your wishes. Yeah. Thanks.
Thank
So, Evan, over to you.
Yes, ma'am.
I'll leave the call then. Thank you. Yeah.
Okay. Thank you, sir.
Okay, yeah.
Yes, I hope my screen is visible.
Yes.
And can someone just confirm once I'm doing full screen, it's working fine? 1 minute.
No. Yes, it's working fine.
Okay. In full screen also it's working, right?
Yeah, it does work.
Okay. Just give me a second.
Sure.
Just a minute. Okay. Yeah. Yeah. So good afternoon, everyone. I am Evan Fernandez. I'm a research assistant with FOSSEE IIT Bombay. And now, since you have seen what exactly is porous media and all, so I'll just briefly.
Evan, sir?
Yes.
Are you presenting your screen?
Yes, I'm presenting it. When in full screen, I think it has a problem, right?
No, we cannot see the screen, sir.
Okay. 1 minute. I'll not go into full screen then. I'll present in the small screen only. Yeah. Now it's visible, right?
Yes.
Okay. So again, good afternoon. So for porous media, there are many examples, as Professor Anirudh said that most of us are porous. And if you want to see a physical example, then you have filtration systems, you have sea foam and all of those things. You also have acoustic dampers. So people who are into dampening or acoustics, they know what is an acoustic dampener. And you also have ceramic filters. Those are again in heat transfer applications, you will find all of these. So these are a few examples of porous media. And now for this hands-on session, this is the problem statement. So we have a flow over a simple cylinder. Now this is going to be a porous cylinder. So over here, there are some base parameters that I have kept. So you have velocity set to 1 meter per second, and your viscosity has been set in such a way that your Reynolds number is around 200. So it's not something really large, because since this is a demo case, it's fine. If you want to run a higher Reynolds number case, then you can obviously tweak these values. And the cube itself, or the object that we have, the porous object, that is going to be at the origin, and everything, the entire domain is modeled around it. So you will have, this is your entire domain size. Now, this is the case structure. So again, in OpenFOAM, we've seen in the past a few sessions that you have zero constant system. So these are your main folders that you will have. So again, your zero is your initial boundary conditions. Then you have constant, those will remain, those are all your properties that remain constant throughout your simulation. And then you have the system block, that is where you have your mesh, your solver parameters. And in this case, we will also have something known as topo set. That is where you will define a zone or a region in your entire domain. Because in your previous cases, you must have seen that when we were modeling, say, that airfoil case using SHM or Snappy Mesh, the airfoil itself was hollow. But in a porous case, you require the mesh in your domain as well as in your object. So that is where topo set will come into play. Okay. Yeah. So again, the FV options in constant. Now this case is for OpenFOAM 2412. So the file name or the file name is FV options. Whereas if you're going with an older version or the ORG version, so those have FV models. So the file name is a little bit different, but the functioning within each of these is exactly the same. So for this particular case in OpenFOAM 2412, the porosity parameters will be set in your FV options. And again, as I said, that the zone that we will define, your cube or your object itself, that will be done using topo set. So we'll see how we do that exactly. Okay. So the very first thing, directly instead of diving into the porosity part, we will first understand what is topo set, because you will have to first define your geometry. So you can download the case. So I've uploaded the case over here in the drive. So under day 2, you can go to day 2 and you can go to porous media. So again, Paris can, I think, share the drive link in the chat, and same goes for the YouTube chat. So within this, you have all of the files. You have the PPT. You also have Professor Anirudh's case. So he was saying that he's modeled ICOFOAM. So you can download this case as well after this session, and you can check. Now his case is a modified ICOFOAM. So as we saw in his PPT, that he had modified a pre-existing ICOFOAM that we used yesterday. And within that, he's created some additional parameters that you can physically put. So instead of adding it, you'll see the difference between the tutorial case that is already present in OpenFOAM, whereas his case that he has made from scratch. And there's also a case study by Jonathan. He was one of our previous interns. He has also worked on a porous media over a cylinder. So he's done a study on various how does the porosity affect your actual parameters like CL and CD. So he's done a flow over a solid body. Then he's also done over coated cylinder and a proper fully porous cylinder. So you can check his case out. There's a report within this zip file as well. For this particular hands-on, you will have to download the porous blockage zip file. So within this, you have all of the case files. So this is a simplified version. I've made some modifications. That's why I'm telling you guys to download this. You can also, if in case you have any problems with downloading this case, I'll show you where exactly the tutorial as well. So you need not do this. I'm just showing you. So once you download the porous blockage zip file, extract it and copy the file into your run directory. So you can do this while I explain where exactly is your tutorial file. So for tutorials, if you want to find this exact tutorial, you can open, now in this case, I'll just open a new tab. You can go down to Linux on the left-hand side, go to Ubuntu. Once you go into Ubuntu, so for OpenFOAM 9, 10, 11, 12, whichever ORG version you're using, those are under OPT. So under OPT, you can go, so in this case, I'll show for OpenFOAM 12, because it's a little bit different. So for OpenFOAM 12, you have tutorials, and under fluid, you will have the not this fluid, but incompressible fluid. Under incompressible fluid, you will have the porous blockage. So this is the exact same tutorial, but this is for OpenFOAM 12. So this is the path that you can follow: OpenFOAM 12, tutorial, incompressible fluid, porous blockage. And you can copy this in case you are not able to download from the drive. I'll also show it for OpenFOAM 9. For OpenFOAM 9, it's a bit simpler. Again, tutorials. In this time, you have to go into incompressible, and you can go to piezofoam, laminar, and again, over here you have the porous blockage. So for OpenFOAM 9, it's going to be OpenFOAM 9, tutorials, incompressible, piezofoam, laminar. And the actual case that we are going to be running is for OpenFOAM 2412. So those tutorials are under user, lib, scroll down all the way to OpenFOAM and 2412, and again, tutorials. So under tutorials, again, you have incompressible and piezofoam, laminar, porous blockage. Okay, so this is the exact same tutorial that I will be demonstrating, but I have made a few changes in this particular case in the zero file, because some of the boundary conditions were not added. It's linked in a way that OpenFOAM understands. So I'll show you what exactly is the difference as well. Okay, so this is your case. So once you've downloaded it, unzipped it, and put it in your run directory, you should have a zero constant system, and you will also have an all run and all clean file. I'll explain this towards the end of this session, what these files do. Okay, so yeah, coming back to the PPT, this is the file structure that we have, zero constant system. Within that, all the files that you have. Now, within the system folder, as you saw in the file structure, you have toposet. Okay, so you can open toposet and keep. So when I'm explaining it, you can keep toposet on one side and you can keep the PPT or my presentation on the other side. So it'll help you better understand this. Okay, so you can keep this file open. I'll explain in depth what exactly is each line doing. So when you start off with toposet or with a porous body or a porous simulation, you have to mesh your domain. Along with that, you also have to mesh your geometry. So that is where toposet comes into play. So say you have your domain, in this case, the rectangle in blue, and we mesh this. Okay, so now this is a simple mesh. It's 16 by 10, the number of cells. Now what we'll do in toposet is we'll first take a group of cells where a geometry we want to define. So in this case, I want to add a geometry or a square towards the, or in the center of my domain. So I will define, or I will collect first these cells. So I have 4 by 4. So these cells I have collected, and once I have collected these cells, I will collect. I will assign this a zone. Okay. So first you will select the number of cells that you want. Then you will assign a zone to those cells, and once that is done, you have your porous, or you have your zone. That is, so you'll have 2 zones now. So previously you had only done your meshing in the outer domain. Now in this case, you will also have another object, that is your square in red. So you have now 2 zones. So you'll have this. So the blue one is zone 1 and the red one is zone 2. Okay, now you don't have to define zone 1 and zone 2. You can only define one zone, and you can add the boundary conditions, or you can add porosity within this zone. I'll show you how that happens as well. So this same example, now I'll explain using toposet. So if you have the file open on the right hand side, you can correlate with this. So this is the very first block. So you have this block, okay, under actions. So the very first thing is you define the cells, as I said. So first you will add a name. So in this case, we have the name porous blockage cell set. So the cell set is just setting up the number of cells that you want in a particular region. So in this case, this is our square that we want to set up. So we have a name, porous blockage cell set. Okay, so remember the name because it will be used in the zoning part. Once you have assigned a name, you will assign a type. So the type over here is cell set because we are setting up the number of cells, or we are accumulating the cells within your domain. So in this case, we have cell set. Again, types are, there are n number of types over here. You have cell set, you have cell zone set, you also have face set. So again, I will show, there's a table at the bottom that you can refer to. So again, type over here, we have cell set. The action that we are doing is we are creating a new zone. So the action will be new. You can also delete something. So say if I have the actual square, and if I want to delete, say, the 4 cells within this in the center, I can also create another cell set and delete those cells. So that can also be done. Okay, so again, the action will be in this case new, and the source will be box to cell. So since we are creating a square, you have the source type box to cell. If I were to create a circle or a cylinder, I can also use cylinder to cell. So there are multiple options again. So first we will do a box to cell. We'll create a square cylinder, and then later on I will show you how to modify this square cylinder into a circular cylinder and run the case. Okay, so for now you have the source type box to cell. That is because we are creating a square, and then we give the dimensions of this box. So we'll give the lower limits. So that is this point, X, Y, Z. And we will give the upper limit, that is this point, the X, Y, Z. Okay. And once you are done with assigning or defining the cells, you will then go ahead with the second block, that is defining the zone. Okay. So this was for sets. and this one will be for the this one is for cells, this one is for the zone. Okay, so in this one again you add the name. Now this name that you assign over here for the zone, this is the same one that you will be using in your FV options to define porosity in that zone. Okay, so this is going to be your zone name, and over here again the type that we are doing, what type of zone are we setting. So this is a cell set or a cell zone set. So it is a set of cells that we want to assign it as a zone. So previously we had only done cell set. Now in this case we are doing cell zone set. Okay, so in the beginning it's a little bit confusing, but other than that it's really simple once you get a hang of it. Okay, so don't worry about that. There is also a tutorial on toposet only, so you can refer to that as well on YouTube. It's there, so that's not a problem. Okay, again action new, we are creating a new zone. So again the action is new. You can also delete a zone, you can subtract, add. There are multiple options for that. And then you are using source. Again, this is the source type that you're going to use. You're going to assign the zone using the cell set that we did in the previous block. Okay, so in this case we are doing set to cell zone, and for that we are using the previous name. So you see that the name was porous blockade cell set in this block. So this was the name. So we are saying in this block that we want to assign a zone and use the cells or use the block that we have assigned everything, that is from this one. So this last line is just referring to all the data set within this block. Okay, so first you define a cell set, or you accumulate the number of cells that you have, and then you assign a zone to it. So that is what these two blocks are doing. Okay, this is the example for the sphere one. So for sphere it's a little bit different. You only have to do this for the cell setting. You don't have to do it for a zone. The zone setting is the same for a cylinder, for a sphere, or for even a cube. It's all the same. It's just that when you're setting up the cells, it's a little bit different how you define those cells. So again, the name remains the same, cell type that remains the same. Action, if you want to delete, subtract, or add a new one, you can do that. Source will change from box to cell. In this case, it will become cylinder to cell. And over here, you will define your starting point. So P1 is 0.1. So you will give the coordinates of your 0.1, and you will use P2, that is your coordinates of your 0.2. And then you will give the radius. So how large you want your sphere or your cylinder to be. So in this case, radius is 0.5 because our square is 1 meter. So we have in this case 0.5. So 0.5, 0.5, it becomes 1 meter in diameter. Okay. Now these are some of the types of set and source for toposet. So in this case, you've seen cell set and cell zone set. So these are for setting up the number of cells or creating a volume or a zone. You can also create faces using toposet. So in case you want to create an inlet face or an outlet face, and you haven't done that in BlockMesh, you can do it using toposet as well. There are also different types of sources. So again, you saw box to cell, that was the one that we used for our square cylinder. And you also saw the cylinder to cell, that is for a circular cylinder. Okay, so someone asking what is P1 and P2. So P1 and P2 are 0.1 and 0.2 for the cylinder. So let me explain this in a much better way. So let's go to paint. Okay. Just give me a second, okay? Yeah. So this is, say, your domain. Now, obviously, in OpenFOAM, since we're solving for FVM, it's going to be a 3D geometry. But in the Z direction, we assign just one cell. So what P1 and P2 does is, you say this is my cylinder, okay? And I will have a second cylinder in the back, okay? Or I'll put it in another color. Okay, so now the yellow one is my back face and the blue one is the front face. Okay, so P1 is just going to be 0.1 for, say, the front face. Sorry. P1 is going to be for the front face, the point for the front face, and P2 is going to be the point for the second face. So that is what P1 and P2 is doing. Okay, that's why you see the coordinate system. So you see this one is at XY coordinate 0, and then in the Z direction it is in -1, whereas this one is in the Z direction at +1. Okay, so this is just points 1 and points 2 in the negative Z and positive Z. That's it. And radius then is again your radius. Yeah. So as I was saying that these are the types that you have. You've seen cylinder to cell, we've seen box to cell. There is also cylinder annulus to cell, so that in case you want to create a geometry like a pipe, so you have just the pipe walls and you have the pipe hollow inside, you can also do that using cylinder to annulus. Okay. Okay, so defines. Yes, radius will define the width of the cylinder, and your points 1 and points 2 will define the length of your cylinder, if that makes sense. Okay. So in this case, P1 and P2 are just going to give you this direction. So depending on how you set it, and the diameter or the radius is set by the actual radius option in the block. Okay. So again, over here in case, and there's also one option in which if you don't know what are the types that are there in OpenFOAM, you can just type banana, or you can type your name as well. So in case I don't know what to add for type cell zone, I can type over a banana and it will throw an error. Okay, so in the terminal it will throw an error saying that this name is not defined in OpenFOAM, and it will give you a list of what can be put in this type. There is also other ways. There are in total 3 different ways that you can try to search this. I'll show you at the end also how to search a particular type in OpenFOAM. Okay, so one of the very rudimentary ways is to just type banana or type your name, or just make a spelling mistake and it will throw an error and give you what type it is. Okay. Now this is about topo set. Okay, so in topo set, first to create, again just giving you a recap, you first create the cell set, or you define the number of cells or the amount of cells you want, and then you define the zone by using the cells that you have already selected. Okay, so this is for topo set. The next thing that you can do is you can go back to the constant folder, and within constant you can just open the FV options and keep it open. So the FV options is going to be the files where you specify all your porosity parameters. Okay, so this is your porosity 1 block. You can also add. So for people, someone was asking on YouTube, how can you define 2 different porous zones? So in topo set, first you can define, say, zone 1. So you can select the number of cells of zone 1, create a zone, name it zone 1 or porous blockage 1. And then you can also select the number of cells for the second zone and define it as zone 2. And then in FV options, you can set porosity similarly. So porosity 1, and you can define the cell zone. And you can also define second porosity. So porosity for the second zone, and you can define the porosity in that as well. So you can have 2 different porosities in the same case. Okay, so first let's look at this block. What exactly is happening in this file? Okay, so this is the file that I was showing you just now. So this is the porosity or the FV options file in which you specify all your porous parameters. Now in this, you have firstly the porosity block itself, that is porosity 1. And this is the continuation towards the end. You have a coordinate system. Okay, so let's look at each line one by one. What exactly is it doing? So under porosity, the very first line you would have is type explicit porosity source. So again, someone was asking about you are adding a source term, but it's a sink term. So what Professor Anirudh meant was in OpenFOAM or in CFD, when you add something new to a pre-existing equation, we say that that is a source term, because that is a new term in simple terms. Source and sink are 2 different terms, and they are not related to what we mean by source term. Okay, so this particular source term is just an additional term to the pre-existing equation. So in this case, we have the momentum equation, and we are adding the porosity source explicitly. So that is why you are using explicit porosity source. So in this equation, we know that U is your velocity, P is pressure density, nu is your kinematic viscosity. So those are all the things that we have added in the transport properties. You must have seen in the cavity case. So that is where you add all of your transport properties. I'll open that as well, so don't worry about that. And SP over here is where you will add your porous resistance. So as Professor Anirudh said, that porosity is just a resistance to a flow, and how much is it allowing the flow to pass through. That is what your porosity in CFD is doing. Okay. So this is a very simple case. So there are additional things that Professor Anirudh said that you have to take care of. So again, I will highlight those in this particular case, why exactly you have to keep that in mind. Okay. So with the very first line is you have the type. So in this case, you have explicit porosity source. The next thing that you do is you will now define all of the parameters that you have to set for this. So you have explicit porosity source coefficients. So all the parameters that you require for this particular equation, or to solve this particular equation or the term that we have added, you will add all of those parameters. Okay. So the very first thing is selection mode. So the selection mode over here we've set to cell zone, because we have already a zone created by toposet. So we will just assign that zone over here. So selection type is, or selection mode is cell zone, and the cell zone is porous blockage. So if you remember in the toposet file, we had named this particular zone as porous blockage. Okay. Now that same name we are going to use in the porosity part. So I'll show you what exactly happens when you're doing this. I'll just run this case quickly. So let's open this in the terminal. WSL. And this one is for OpenFOAM 2412. OpenFOAM 2412. So first I will do block mesh. I will generate my background mesh, or the actual mesh itself. So we have, so I'll just show you what exactly is happening. Okay. Yeah. Okay, so before running, I just change this to 0.org, otherwise it may cause problems. Yeah. Okay, so let's try one thing. I'll just switch to OpenFOAM 9 and try using the paraform that is built in that. Okay, there seems to be some problem. Try built-in. Okay.
Maybe you can open Paraview.
Yeah.
Yes.
This switch is back. So let's do touch fdp.foam. Let's open. Okay, there seems to be some problem with the Paraview itself. It's opening in the background, but it is not displaying anything.
Maybe what you can do is in search bar you can search for Paraview.
Yeah, I've done that only. I opened Paraview manually.
It's the Ubuntu one.
Okay. Okay, Paraview, I don't have it installed separately.
Paraview must be down there.
Okay, never mind. I'll try to explain it this way. It's fine. So the very first thing I do is create a block mesh, and actually I have to show toposet, because then it will make much more sense. Let's see. I'll give it one more try. Try OpenFOAM 2412, and then I'll just do toposet. Try closing a few tabs. Okay. Okay, let's see what we can do. Yeah. Okay, so what you do is first you do block mesh, And once you have created your background mesh, you'll be able to see that it's properly meshed. You have just a simple domain. Within that, we will assign the cells. So for that, you can use a toposet. The command is toposet that will generate, or it will generate your zone. So again, I wanted to show you that, but my paraview isn't loading properly. So let's check that later on. Yeah. Okay. So what that toposet will do is it has created already a zone that is your porous blockage. Okay. And in the porosity block that we have over here, we will be assigning, or we will be assigning the values to that particular cell zone or that particular zone that is porous block. Yeah. So the next thing is your type. So within this, you will have the porosity type or the formulation. So in this case, as Professor Anirudh explained, this is your Darcy-Forsheimer formulation. And you also have another formulation that was the Darcy-Brinkman-Forsheimer formulation as well. But again, in OpenFOAM, you just have this particular formulation over here. And it's only going to be using two terms. That is your Darcy resistance term, resistance tensor actually, and your Forsheimer resistance tensor. Okay, so these two values are only going to be used over here. In case you want to use any other model, you might have to do some solver modification. And also over here, there is no interface model available in OpenFOAM. So again, if you, as Professor Anirudh pointed out, that people just add these two values and they start running simulations and they expect and they publish papers. So you have to do proper validation in this case. So whatever paper you're referring to, always validate it against the values that you are getting. And in case you have to model any interface or any other model that is already present or not present in OpenFOAM, you may have to go into the source code. So that is why I've also attached Professor Anirudh's case in the drive. So for people who are more interested in porosity and know what they're doing, they can try modifying a pre-existing solver in this case. Okay. So for this case, you just have the type Darcy for Scheimer. So this is the equation that it is solving. So the SP term that we added in the momentum equation, so this is the exploded version of it. So in this you have mu du, and then you have half rho f, and then again you have velocity. So your mu is your dynamic viscosity, d is going to be your Darcy resistant tensor, and f is going to be your Forsheimer resistant tensor. So again, you will see this when we add this in the next part. So again, this is just a continuation. So you have the type Darcy-Forsheimer, and you also have some values that you set. So in this case, you can see over here, cell zone we had set porous blockage, type we had set Darcy-Forsheimer, and then you specify some values over here. So already in the tutorial, you have some of these values and they give you what exactly it does. And let's see what actually it is doing in the equation. So in this case, the very first thing you will see is D is equals to 1000. And then we have the actual term. So over here, the capital D that is there, that is just a placeholder. And this D is your resistance tensor for Darcy. Okay. So keep that in mind. So this small d is which will actually affect. This capital D is just a placeholder that we have added. So we don't have to type 1000, 1000, 1000 every single time. So you just have to make one change and it will be carry forwarded over here. In case you want to apply, now in this particular case, the porosity is added equally in the X, Y, and Z direction. You can see this from this exploded version. So this is just the tensor version of it. So you can see that it is in the X, Y, and Z direction. And when you add it to the equation or to the term that we had in the momentum equation, you get this particular thing. This is if we are ignoring the Forsheimer term. Okay. So again, you saw that in this particular equation, you also have the Forsheimer term. But if you ignore that, you will only get this value. Okay. So again, this is a linear drag force, as Professor Anirudh showed you that. And in case you want to change the directions, I'll show you how can you do that as well. So in case you want to change the direction in the X, Y, or Z direction. So say you want to have the maximum resistance in the X direction, but allow flow in the Y and Z direction. In that case, you can also do that. The next thing is permeability. So Professor Ainud also showed about permeability. How is it related to porosity? In OpenFOAM, this is a very simple relation. So he said that the term itself is proportional or inversely proportional to the permeability. And in this case, one is just the length that is there. So you can replace all of these and you will get the relation. So in this case, when so just keep in mind that this is not the Darcy number. Okay, so Darcy number is different and the resistance term that we are adding over here is completely different. Because if you take that relation what he said and you try to relate to this particular equation over here, it will be that he has said that as you increase the number, your permeability will decrease. But in this case, as you increase the number, the permeability will the larger the value for D, it will decrease, whereas he had said that it will increase. So that is the thing, that it's completely different. So just keep in mind when you're adding it in OpenFOAM. Okay, so this is not a Darcy number, this is just the Darcy resistance tensor that you're adding. So you're adding a value for that. So again, the higher the value, your permeability will be smaller and your blockage will be higher. So higher value, higher blockage. It's that simple. Okay. So coming back to the block itself, so over here we've set a value of 1000. So that is a fairly, it's a block that isn't that porous in simple terms. So it won't allow a lot of flow through. So if I were to set this number to say 100 or 0.1 or something like that, it will allow a lot of flow through. We'll make those changes and we'll see how does that affect the whole simulation as well. So that is about the D part in the entire equation. And then comes the Forsheimer part. So as he said that you have two parts. One is the viscous force that is governing, and then second one is the inertial forces that is governing. So the Forsheimer term over here is just checking that. It's checking the initial losses that you have. So 0 over here is just meaning that there are no initial losses, because the Reynolds number itself is also low. When you increase your Reynolds number, so if you're at a higher Reynolds number, that is where your Forsheimer terms will play a bigger role. In this case, even if you add it, it's just going to be a negligible difference. So that's why we've set it to 0. You can change it. Again, this tutorial is given to you. You can make changes. You can run it and see what differences does it affect you. So since we have kept this particular term as 0, so this is the equation that we had. So this entire term becomes 0. If it were a non-zero value, then you would have the source term as a summation of both the Darcy coefficient or the Darcy term and the Forsheimer term. But in this case, since only one term is there, so everything is based on just the Darcy term. So that is why your source term is based just on D, and higher value of D will this result in higher resistance and low porosity. Okay. And lastly, then you have your coordinate system. So that is towards the end over here, coordinate system origin 0, 0. So we haven't added any rotation. So this is just to add a rotation. So as I was saying, that in case you want to add the porosity in the X direction to be the maximum, so you don't have a lot of, so you don't have, yes, please.
Sorry to interrupt you. Just go a little bit slow.
Okay, fine.
Yes.
So I was saying that since, okay, I'll just go one slide back again. So as I was saying that the Darcy Forsheimer, it has two terms. So you have the D term and the F term. So again, now since in this equation we have kept the F term to 0, so the entire simulation will be just based or governed by this particular value of D. So that is what I've written over here. The source term will be based on D, and higher value of D will cause higher resistance and low porosity. Okay. Then this is the coordinate system for rotation. So in case you have the value, so now in this case we have set it uniformly. So we had set it 1000, 1000, 1000 in the X, Y, and Z direction. That means porosity is equal in all three directions. But in case you want high resistance in the X direction and low resistance in the Y and Z direction, that can also be done. And if you want to change this orientation, or you want to change the way it works, so you can always change this rotation part. So these are very significant in now if you've ever seen a honeycomb structure for wind tunnel testing, that every time the flow passes through that, you will get a laminar flow that is uniform and parallel to each other. The flow is always going to be parallel to each other. So in those cases, if you want to simulate something like that, you can always use these rotation values, and you can also change the value of Darcy, the Darcy resistance term, in such a way that you always get a linear or you get laminar flow in a particular direction. So that can also be done. So again, this defines your local coordinate frame, and can be used to rotate the resistance directions. So that is what this term is doing. So yeah, before going to searching this, let's go back to the case. So now in this case, I have ran just block mesh and I have done topo set. Let's try one more time. I'll just try to close one tab and see whether that is affecting it. Let's try and see whether parafoam opens. Okay, so there seems to be a problem with parafoam. Without that, I won't be able to show you what exactly is happening. Paris, can you do one thing? Can you just download the files and just run it? I will explain it from your ParaView, because mine, it's opening, but it's not loading anything.
Okay,
yeah. So for running the case, it's very simple. So again, let's just close this. So until Paris runs the case, Paris, you can do an all run. The file is there inside.
Yes.
Yeah. So until he's running that, I will show you how to run this case. So the very first thing you can do is, so now say you have a clean case. So I hope that none of you have run the simulation. If in case you've run it, it's fine. So first you will do is do block mesh. That will create your mesh. And on top of that mesh, you want to assign a number of cells and create a zone. So that is where topo set comes into play. So you will just type topo set and press enter. So over here, it will give you some value saying that the mesh is created. So it created a cell set named porous blockage cell set, and it also created a cell zone. So now in your ParaView, if you open it, you will be able to see a zone. So again, if you're on OpenFOAM 2412, you can click on a button that will show you zones. By default, it won't show you zones. So you will have to click that button. So that is where you will be able to see your porous blockage itself. Once that is done, you can then start to run your simulation. So this was based on the piezofoam solver. So you can just type piezofoam and press enter. So it will run up to 100 seconds. So that is your iteration. So your start time, end time is all set in your control dict. We haven't changed that because even if you change the delta t and all, since the simulation is quite coarse and quite simple, it makes no difference in changing those values. So once you've run piezofoam, you can do parafoam and you can open the file. You'll be able to see the flow and the flow pattern over this. Now, since mine isn't working, so I'm not sure if it will work. Let's see once more. Yeah. No, it isn't working. Paris, have you completed that?
Just a second, it's almost done.
Okay. Yeah. So for people who have completed this, you can open it in ParaView and you know how to apply it and run the simulation. You can do that. So that is one thing. The second thing is you can change the values for the Darcy resistance tensor. So that can be done. So again, you can use any of these values. So you can type your own value as well. So if you want, you can change this to 10,000, 100,000. That's fine. So it will become more of a bluff body rather than a porous body if you increase this value. Whereas if you decrease this value, it will allow flow to just pass through. So at 100, you'll be able to see that the flow is passing through the cylinder with very little resistance, and your vortex shedding that happens behind a proper cylinder will not be seen over here in this case for D equals to 100. Whereas for 200, 500, you'll be able to see a little bit fluctuation, but again, those are all negligible fluctuations when compared to 1000. So you can try this. You can run it for D100 or D200 and see the difference. Once Paris displays the screen, I will show you how to check for streamlines as well. Yeah. And another thing is we will then, once you have done this, yeah. Okay, so Paris is sharing. Yeah. Yeah, so Paris, you can do one thing. Yeah, so once you have clicked on apply, you're on OpenFOAM 2412, right?
Mm-hmm.
Yeah. So on the left hand side, you can see that, just scroll down a bit. Okay. Okay. Can you switch to OpenFOAM 9 just for viewing in ParaView?
Sure, sure.
Yeah. Because ParaView in OpenFOAM 9 is much better when it comes to seeing zones.
Okay.
I hope everyone is able to see Paris's screen.
This will not work. Okay. I have to copy this case. Okay, just a minute.
Yeah. Yeah, so after running block mesh, so once you run block mesh, you can run topo set. I'll type the command in the chat. So I'll first you do block mesh, then you do topo set. And then you do PisoFoam. Once you've done that, then you can do lastly parafoam. Okay, I'll stop sharing my screen. Yeah, so I hope Paris's screen is visible now.
This tutorial was for 2412, right?
Yes.
Okay, that is the reason it is giving error. Wait, parafoam hyphen in. Okay, so I have to just show the 2412 part. Okay.
Yes.
Understood. Yes. Whereas block. Default run porous blockage.
Yeah. Okay, so on the left hand side there should be an option to read, yes, to read zones. Yeah, if you just throw an error in the beginning saying that it cannot calculate data set. Click to VTK blocks. Yes. Okay. So see, you can see over here and switch to mesh mode, please. Yeah. Okay. So see, this was the mesh that we created. So your domain was created using block mesh. In that we have specified the number of cells in X, Y, Z direction. And once you have done topo set, it will create this red zone over there. So in that we have assigned a box to cell. So we've given a minimum distance and the maximum distance of the box. So it has assigned it based on that. So any cell within that region will be assigned as zone or porous blockage zone. Okay. Now, Paris, can you just run the simulation up to the last time step?
Yes. In this, in mesh part only or velocity?
In velocity.
Yes.
Okay. Okay, so now since the value for the resistance was set to 1000, so this will behave as a proper porous cylinder. Okay, so you can see, and Paris, can you switch to streamlines now? You can close the mesh.
Yes.
Streamlines and switch to circle, and this should be around 5. Point cloud and radius of 5.
That's radius.
And the number of points set to around 10,000 or something. Yeah. 1,000 will be less, 10,000 will be a little bit more. Yeah. You can close the sphere itself. Yeah. And the foam.foam file, just switch that on and change that to edges instead of surface, featured edges. Yes. Yeah. Yeah. So just zoom in a little bit. Yeah. So as you can see, Now, since this was set to 1000, still there is a little bit flow happening into the object itself. But as Professor Anurudra pointed out, that near the interface, there technically should be some resistance. It should be more than the actual block within the block. So that is not being captured over here in OpenFOAM. So in those cases, if you want to capture that properly, you will have to model your own interface equation, and you will have to plug it into OpenFOAM. So now the good thing about OpenFOAM is that the backend code is easy to access. You can open it, you can make modifications to it, and there are also tutorials by us on how to modify a solver, so you can check those out. And in case you want to modify any of these, you can do that using OpenFOAM. So that is one added advantage that you have. Now, Paris, can you just close this and do the same thing, but change the value for D to 100? The same simulation under constant. Yeah, constant FV options. Yeah. So now we'll change it to 100 and see what is the difference. Commit out D1000.
Okay.
And to put D100.
10,000.
Yes.
Achha.
D1000, just comment that and switch to D100.
Okay.
Yes.
Okay.
You can save this and you can run it.
Okay.
You'll have to close Paraview.
Or should I directly do run?
You can do this dash all run. Okay. Hit run, right?
We have to
remove the log file. Just do a all clean. All clean file is also there. So in your files, when you're seeing the files, you'll see that there's an all run and all clean. So those files can run individual commands that we do, like instead of doing block mesh, topo set, then your solver name, instead of doing all of those one by one, there's a script that runs all of these things for you. So you just have to type one command, that is bash./all run. I'll show you how to do that as well. So once you've done that, it will run your simulation in that order. So you can open that file, you'll see that it will have the first command named block mesh, then you have topo set. So what you would type in your terminal, you can type it in that one script and then automate it using that. You can also clean your entire simulation. So if you've done, in this case, how you saw that we have done the simulation and you want to clean that to run a new simulation, you can use all clean, or you can also do foam clean tutorials. So again, that also I'll show. Switch to Streamlabs, please. $10,000. And you may have to change the background. I think it's white on white. Yeah. Put it to 10,000. Okay. And the same thing, the foam.foam file, change that to featured edge. Yeah, thank you. So you can see that in this case, the flow is happening directly through the object. That means it's extremely porous. That is why there's very little resistance, and you can see that there's no vortex shedding also behind the object. Now, in this case, you can create a porous object in such a way that if you have turbulent flow coming through the inlet, it will make it laminar. So those cases also can be done using these models, and you can use these parameters. So in your XYZ coordinate system, you can allow that to happen. You can change that in a certain way. Now this is just uniform porosity in all the three directions. That is why you can see that it makes no difference. Okay, so this is a way you can simulate porous cases in OpenFOAM. Now I'll show you how to change it for a circular cylinder, and then you can run it on your own. Yeah, Paris, thank you. You can stop sharing.
Thank you, Answer.
Yeah, sorry for the inconvenience, everyone. Yeah, so I'll share my screen again. Yeah, so in For the circular cylinder, now since you have already run the simulation, you will have all of these files. So you can clean the case. Let's close this. So if you want to clean the case, there are two ways. If your file or your folder has this all clean file, so you can open this all clean. So you can see that this all clean, it has a simple script in the beginning to just let OpenFOAM know what we are trying to do. And you can then run the command clean case. So that is what it will run. And same goes for the all run. So all run over here, it is restoring zero directory. So in case you have named your folder as 0.orig, it will rename that 0.orig to 0 folder. So that was from the tutorial itself. So that is why this is there. And then it will start running one of these commands. So it will first run block mesh, then it will run toposet, then it will run the solver that you are running. So in this case, PiezoFoam. You can also add another line to directly open parafoam. You can run application over here, and then you can just type parafoam. So you can run this, and once your entire script is done, means once the whole simulation is done running, it will then launch parafoam. So in this case, I don't do that because my parafoam isn't opening. Okay, so you can do this. You can run this script simply. So if I want to clean the case now, I can use the command bash / all clean. I'll just zoom in a little bit. You can see it. Yeah. So you can run this command bash / all clean. Once you run this, it will give the command saying, it will give you a output saying cleaning case, and then it has cleaned the case. So now if I load my case back again, it will only have 0 constant system. Even the mesh files and all of those things that were there, it was deleted. The poly mesh folder that is generated, your mesh files remain. Okay. And if I want to run this case again, but now first I have to make the changes. So the very first thing you will do is, so this is for this part, just follow along with me. But go to your system folder and open your toposet directory. Okay. So go to system, toposet, and open that. Now in this, we will change the source that is in your first part from box to cell to cylinder to cell. Okay. So we will change this to cylinder to cell, and you can delete off this part. Okay. So over here, now you will type P1 and you will give the coordinate system. In this case, it is 0, 0, -1. And we'll add a semicolon. Let's just cross check whether the colon is there or not. Yeah. Yeah, so there is a colon. Okay. So you can do P1 and then give the 0.1 coordinates, write P2 and give the second coordinates. So again, this is 0, 0, but this is in the +1 direction. And then you type radius, and then you type the radius 0.5. Okay, so you have to make these changes in your toposet. Okay, Paris, can you just make these changes as well?
Sorry?
Can you just make these changes as well in your toposet?
Yes. Yeah. Just.
So first you will, so I'll again repeat this. You can open your file folder. In your run directory, you already have your porous blockage. Go to your system folder, then go to toposet, open toposet, and in toposet under the cell set cell block, you type in this instead of source box to cell. So first you do is you change box to cell to cylinder to cell, and then you change, you can delete that line that says box and the values for box, and you have to type in P1, that is 0.1, and you type the coordinate for it, 0.2, and then you type the second coordinate for it, and then you type radius and you give the radius for your cylinder. Okay, so this is the block that you have to make. So has everyone done till here? Okay, great. Yeah. Okay, so once you've done this, you can save your file, and then you can just run again the whole thing. You can either do bash all run. So you can type the same command bash. Instead of all clean, you can do all run, or you can manually type in block mesh, toposet, then PiezoFoam, and then ParaView. You can do that manually, or you can run this command as well. So if you run this command, it will do this. Okay, so it says that no 0.orig, so there's no file to restore, but it has run block mesh. So it ran block mesh, then it ran toposet, and then it ran PiezoFoam. Okay, so once you are done this, you can then open ParaFoam and you can view the circular cylinder. So now instead of a square cylinder, you will have a circular cylinder. Yeah. So Paris, have you done that?
Yes, yes.
Yeah. So can you open that? I'll stop sharing my screen.
Yes, yes.
Yeah.
It is visible, right?
Yes.
I have made the changes.
Yes.
I have to run 2%.
Block mesh and then toposet. Yeah. So you can see now, since the mesh is extremely coarse, that's why it is not a proper cylinder or a proper circle. But if you refine your mesh, you will get a proper circle. Okay. Paris, you haven't run it, so it's fine.
Okay.
Yeah. Just keep it on the zone 1. Yeah. Okay. So if you want, you can put the mesh also on. That will help better. It will explain more better. Yeah. So this is the mesh, and we'll switch to another one instead of VTK complex block index. No. Yeah. Switch to VTK block color. Color at the bottom. Yeah. Okay. Okay, fine. Okay, fine. You can switch to the featured edges only. I think it's not showing them. Yeah, so you get the idea, right? So you can change the geometry based on however you want. So if you want a circle, you want a square, you can use toposet to do that. And if you want to change the values for your porosity, you can also do that. In OpenFOAM, currently the interface part is not there, so that will have to be modeled. So that is one downside of using just the tutorial that is present. But for learning purposes, you can always use these. Yeah, Parisa, thank you. You can stop it if you want.
I'll just run it and maybe.
Okay, fine.
So
yeah. So over here you can see that it's a proper circle. It's not a proper, but a very coarse circle. And yeah, with mesh. Yeah. So you can see, because the cell size are very large, that is why it will just follow along. So there is a way in which toposet understands whether to take that cell or not to take that cell. So again, that has been explained in another course that we had taken on OpenFOAM. So in that you can check for toposet. There is a video available on YouTube. So in that, everything for toposet is explained in detail from scratch. So how to set up a case all the way up to how to running that case. So that can be seen on YouTube. That's fine. For porosity, you can check. You can see this. Yeah, Paris, thank you. You can.
Okay.
I'll explain the code part.
Sure.
Yeah.
Thank you.
Yeah, thank you, Paris. Yeah. So I'll switch back to my screen. Yeah. So again, as I said, in porosity, there are already tutorials available in OpenFOAM. Along with that, in the drive, you will find that there is Jonathan's case and Professor Anirudh's case as well. So I have that also over here. So Jonathan's case is again a circular cylinder in which he has done 3 types of simulations. One is for a solid cylinder, other one is for a porous coated cylinder, and the last one is for a fully porous cylinder. So you can check his report as well. So in this, he's explained everything in detail, all the way from the boundary conditions to the governing equations up to the simulation that he has ran and the results that he's got. So in this, you can see he's created the geometry in gmesh. So that is why he will have a .msh file in his folder. So you can run the command gmsh to foam. So people were asking how to run external meshing into OpenFOAM. So you have this for that.
Ivan, just a second. We have just posted the attendance.
Yes, ma'am.
So I would request you to kindly pause for 1 minute, and I would request all the participants to kindly mark yourselves present.
Sure.
Yeah. And I have also requested all of them to not to worry for the attendance. We will post it in varying times. We will not post it in a particular time, and whenever we will post, we'll announce that we have already posted it in the chat box, so that we all can take a pause and mark ourselves present. We are also putting the attendance sheet on YouTube. So please wait. All the participants who have joined through YouTube, you can also take a pause and mark yourselves present. We are waiting. If you are done marking yourselves present, we can continue with the lecture. Should we start?
Yeah. Okay, so for people asking how to plot streamlines and isotherms, uh, on the last day on Friday, we have a dedicated session for post-processing. That's why everything that we're showing in Paravi, we're not going too much in detail. We'll have that session on the last day, so don't worry about that. So we'll show you how to trace streamlines, isotherms. If it's a temperature case, we'll obviously show you isotherms. There we'll also show you how to do post processing. So if you want to find coefficient of lift, coefficient of drag, all of those things, you can do that using Paraview as well. So we'll show you that. So don't worry about the last about these on. Okay, so on the last day we have a dedicated session. Yeah. So as I was saying, for people who are interested in porosity or want to learn more about it, there are case studies already available in a repository. So one of these is Jonathan's case. So in this, he's explained how can you simulate the whole thing in OpenFOAM. So again, here he's mentioned the boundary conditions that we've used then for each of the cases. Okay, so this one is a boundary condition for a standard flow in a cylinder. This one is for, I think this one is for kinematic boundary condition. Okay, so one was for completely porous. Yeah, so over here he's mentioned for fully solid objects, for porous coated, and for fully porous objects as well. So you can check that the solver he's used is also piezo foam, so it's the same. You can use it, and he's I think done it for OpenFOAM 2312, so it should work with 2412 as well. If there are any problems, it will directly show it in the terminal, so that's not a problem. He's just given the general logic of what is happening in the whole simulation, along with that the equations as well, and the fluid properties in this case. And speaking about Professor Anirudh's case, so this is one. So as he was saying that he has the solver and he has the cases. So if you just want to run the cases, you will first have to, again, it depends. If you want to run the unmodified case, so this is just the lid driven cavity case, the unmodified one. And there's also the porous square, the one that he explained today. So that case is also there. It's already run, so you can directly open that as well. And in this one, he's using a different solver. He's created a custom solver. So that is why you have this name, porous DBF ICOFOAM. So that is his custom solver. You can also check it in the control dict file. So in that, it will show you that the application that he's using, this is the solver name. Okay, so porous DBF ICOFOAM. So again, over here, he has given the code files as well. So for solvers, the unmodified copy is there, and this one is for the actual solver. So you have the C file and you have the header files for it. So the create field files is where he has added those additional terms in your transport properties. So in transport properties, by default, you would only have kinematic viscosity, that is new. But in this case, he has also added LREF, K minimum, porosity floor, all of these parameters. So if you see his case, let's go back to the case. So the porous one. So I'll show you what is there in 0. So in 0, by default, in our case, we only had velocity and pressure. But in his case, he has modeled it in such a way, the whole solver, that you will have to add the Darcy number, the FOSSEE coefficient, and porosity in the 0 folder itself. So you will have to give an initial value for these values. And throughout the simulation, then it will compute that. So you can see he's given the values over here. So it's calculated it. Okay. Same goes for FOSSEE coefficient and porosity. And in the transport properties, constant transport properties, this is where you will add the values new, LREF, K minimum, porosity floor. So all of those things, you can add it over here. So you can open the code. So this was the header files that he has used. So within this, so your header files is just to define what you want to run. So those things have to be done in the header files. And the .c file will be what will be solved during your simulation. So in this case, under solver, the modified solver, porous DBFI COFOAM. So in this one, you can see that he's added over here the additional terms. So porosity effect, permeability K, porous coefficient. So all of these things, they are calculated using these equations. And also during the simulation, so everything within this while loop will be run during the simulation. Okay, so again, this is covered during the solver modification sessions that we have taken in the previous workshops. So if you're interested in modifying a solver, you can check those videos out. So just to briefly explain what is happening over here, if you first added the porosity effect, K, and porous coefficients, you've calculated that, and then you are using your equation. So the equation that you had displayed for the momentum equation, the source term that it's additionally adding over here. So this is the thing. So you have d dt u, d by dt of u, then you have plus, then you have the porosity terms over here, divergence of the porosity with u, then you have also the Laplacian terms, that is nu and your velocity, and lastly you have the additional source term. So this is where you add it. So you have SP, porous coefficient, and U. So if you see that equation that he showed you and you cross check with the things that has been written over here, it's very similar. And one thing about OpenFOAM is that all these codes are top level coding. So you have to just define a value over here and you can then add it in your equation. So that is very simple. You are not doing extreme modifications to the existing code. So OpenFOAM will know that if you type porous coefficient and you just type these values, it has to search for these values if you mention it in the header file. So that is very simple. So you're just mentioning a name and then you say that this name is located in that file, just access that. So that is what is happening in this entire code. Same goes for the equation. So over here he's added for U equation to solve a specific equation over here. So that is what is happening over here. And then the piezo corrector loop. So that is, I think, the same with negligible changes. Yeah, so over here it's the same. So you can cross check it with the actual C file. So this is the original one that is there, ICOFOAM. So in the ICOFOAM, you can see that you have the piezo corrector loop. So that you can cross check with this one. Let's open this side by side. Yeah, so this is the modified one. This is the not modified one, the original one. So you can see there are key differences in the first loop, the first while loop that you have. So this only had ddt, it only had the momentum, this momentum equations for this one, but over here you have these additional terms for porosity as well. So these are some of the key changes that are there with the source term added over here. Okay, so if you have an equation and you want to add it to a solver and create your own solver, that can be done easily in OpenFOAM because the codes itself are available. And in case you don't know what to do, there is also a forum, there is also websites that help you out with that. So on the forums, you can always ask your queries. There are people who have already done something or similar to what you're trying to do, and they will be able to help you out. You can also check the user manual for OpenFOAM. There's a user manual, and there is also a coding documentation for OpenFOAM. So in that, it explains what is FVM, what is DDT. If you want to add if you want to add a single derivative, you can add that. If you want to add double derivatives, how do you program that in OpenFOAM? So that user guide is also there. I will add that in the drive as well under the documentation tab. So you can download those files if you want to do some modification in OpenFOAM. Okay. So this was it about porosity, toposet, even a little bit of solver modification. So usually we take each of these topics separately because they are vast in themselves, but just for this particular tutorial, I've summed it up in one particular session. So if you have any questions, you can ask in the chat. I'll be happy to answer that. Okay, so does anyone have any questions? You can raise your hand, you can unmute. What is the logic behind this? Okay, so yeah, so Samiola, what logic are you exactly asking for?
Actually, I am asking about the regarding the code. In the code, it is written that plus FVM, and in the second line, it is written as a minus FVM. So, what is the why we are using a plus sign at one place and negative sign at other place?
Okay, so if you see the momentum equation, you will have some terms on the left hand side and you will have some terms on the right hand side. But when you're programming it in OpenFOAM, you can keep it as it is. So you can always, if you want to keep the Laplacian term as positive, you can change the side and you can put it to say on, if it's on the left hand side, you can switch it to the right hand side. So that's also possible. So that way you won't have the plus or minus sign. You just have an equal to sign. So that is just the equation. So if you, that's why I said, if you have an equation, you can keep the physical form in front of you, and then you can try to program it based on how now now OpenFOAM is in C++. So the programming is very simple in terms of relating it with the physical term. So you can keep both of these side by side and try to correlate these. So usually it is just terms that have been rearranged in such a way that it makes it simple for OpenFOAM to understand.
Okay, thank you.
Yeah. Okay, Vednath sir, if there is no file as all clear, there should be an all clean folder. I could not run all clear. This file was not found in my folder.
Sorry, I mistyped it. It's all clean. This all clean was not also, it's not there in my folder. I copied it from the default tutorial, not from the drive.
Okay. And which version are you on?
12.
12, right? Yeah. So in OpenFOAM 9, 10, 11, 12, the all run all clean file is not present. In OpenFOAM 2.4.1.2 it is present. So if you want, you can copy it of these files also. So you have you have the files already shared on the drive. So you can download that and copy from that file into your folder. It will work.
Okay, thank you.
Yes. As long as the commands are the same for both of these versions, it runs fine. Okay, so whether you take it from OpenFOAM 23.12, 24.12, or even OpenFOAM 12, it works fine. Yeah, and Paris has already shared one command, so you can also do foam clean tutorials. This is for any version of OpenFOAM that will by default clean your case. It will only keep your zero constant and system folder. And if there are some supporting files, like in Jonathan's case, you saw that you have the .msh file. So those files will also be there. It does not clear those files. It only clears the time step files, your polymesh file that has been created by block mesh. So those files are cleared. The rest everything remains the same. Any other doubts? If not, then we can, yeah. Can we use GMSH for the geometry creation of a complex object? See, Gmesh is similar to block mesh. It's just that you have a GUI for it. Uh, I used to use Gmesh before this. So before using blockmesh, even I used to use Gmesh. So what it is you have a text note or a notepad in that case, and you have to set those values. So it is just that your GUI will help you visualize where your points are, but the usability is similar to block mesh. So in block mesh, you cannot create a heart because the heart is a really complex object. That's why I said if you want to create anything complex, you can use Salom. You can also use Blender. If it does not have accurate dimensions, you can always use Blender, because Blender's dimensioning is a little bit finicky. It won't give you as accurate as FreeCAD or Salom or something like that. So if you have very complex objects, I would recommend you going with Salom or Blender. And for simpler objects, you can always use CF Mesh. You can use FreeCAD. You can also use block mesh, snappy hex mesh. But again, snappy hex and block mesh are all text based, so it becomes a little bit difficult to visualize what you're trying to see. Yeah, there's also ICM, that is of ANSYS, and you can also use ANSYS Fluent. Fluent geometry creation, you have, I think, there are three different. There's Design Modeler, and there are two more. But again, those are all commercial. If you have the license, or if you're a student and your university has that access, then it's beneficial for you. But for someone who's independently working, it becomes difficult because there are limitations on it. Yeah. Any other questions? Okay then. So the afternoon session, we'll have multi-phase flows. That will be by Nikhil. So he's also one of our team members. So he will teach you how to simulate multi-phase flows in OpenFOAM. And once you're done with that, then we'll also have a question and answer session at the end of all of this. So in case you have any questions that has not been resolved now, we can take it later on in the day as well. Yeah. So if there are no further questions, we can break for lunch and we can meet at 2 o'clock. Right, Palman?
Right. So did we check the YouTube also for the questions? Are there any questions?
I have closed YouTube. Paris, is there any questions on YouTube?
Not much.
Okay.
If there are any relevant questions, we can take it. Otherwise, just one more reminder for the attendance part. If someone has missed marking themselves present, I'll just put the attendance once again.
Pranay is live on YouTube. He has answered almost
Okay.
every question.
Okay, great then.
Thanks, Pranay.
And yeah, so Jitendra, Manzil has added a comment on your query. So as I was saying that even Manzil is saying that you can do mapping from images. That is possible in Blender. So you can take an image and you can map it out completely from scratch. So that can also be done. So Blender has those capabilities. Yeah. So the attendance is once more shared in the chat for people who missed.
So for the afternoon session also, I would request you to please join the meeting a bit early, around 15-20 minutes early. Around the 1:40, 1:45, you all can join. We can start at 2 now. So it's just perfectly 1 o'clock now, and we are happy that we are on time today. So we are taking break now, and then joining back at 2. The next session will be by Professor Naren in the second half. So we are expecting it to start at 2. So let's break for lunch now. Thanks a lot.
Hello. Am I audible?
Yes, sir. Yes, sir.
Yeah. Thank you. Paris. Yeah.
Yes, sir.
Yeah. Thank you. Um, Hello.
Yes, sir. Yes, sir.
Yeah. Can I share my screen and check?
Yes, yes, sir. Sure.
Sure, sure.
Yeah. I'm just sharing from another small tab also, because in case the internet is suddenly there is a power down here, so that it will help.
No problem, sir. No problem.
Yeah. Okay. So
Naren sir, we have 80 participants now. We are expecting 100. So let us wait for a couple of minutes. It's 1:59 by my watch now. So for all the sessions, approximately 100 participants are joining. Let's wait for another couple of minutes. So, Mr. Santosh, actually we are recording the sessions, and whatever the faculty members are showing, you can refer to them in those recordings only. So, it will not be a problem if the faculty members are not sharing the PPTs separately. So it's 2:03 now. I think we should start now.
Yeah. Is my screen is also visible?
The screen is visible, sir. So I welcome you, sir, to this session in the day 2 and the second half of the day. This is the third session of this faculty development program, and we all welcome you to this session. And let me just introduce you to all the participants. So we have a majority of faculty members here who has joined, and we have also allowed some students to join. Okay, so before we start, I'll just introduce you to all the participants. Professor,
sure.
okay. Professor P.R. Naren is currently the Dean, Capacity Building and Digital Transformation, Sastra, and Professor of Chemical Engineering at the School of Chemical and Biotechnology, Sastra. He has completed his PhD from Institute of Chemical Technology, Mumbai, in collaboration with National Chemical Laboratory, Pune. Followed by, he has also done 18 months of postdoc at the École Centrale de Lille, France. And his interest areas and specializations include computational flow modeling, process simulation, and development of phenomenal reactor engineering models for multi-phase systems. He has also collaborated with Dr. V.K. Jayaraman, Flame University, Pune, data science group towards exploring the development of machine learning models to predict hydrodynamic features in multi-phase flow contactors. He is interested in exploring and using FLOSS tools such as Scilab, OpenModelica, DWSim, and OpenFOAM for education. At Sastra, he had established the Sastra FOSSEE Center as a partner with IIT Bombay FOSSEE to carry out FOSSEE activities in promoting free and open source software tools. With the formation of Teaching Learning Center at Sastra in November 2023, he is engaged with faculty and students to facilitate transformative teaching learning experience. Currently, he guides two PhD students in the domain of engineering education. He is passionate about learning and making teaching a cheerful and cherished experience. So we all will experience his teaching today, and I'm sure that all of you are going to enjoy it a lot. Along with the informative and interacting part, Professor Naren's teaching is, mind blowing. So over to you, sir. So probably you can switch off your camera while talking so that this bandwidth the quality will be good. You can just share the screen and keep yourself. You know, you don't need to share your video. We can have that. We can participants can see you at the end of the session.
Right.
During the interaction.
Now am I audible?
Yes, sir. You're audible, but your video is still. So I think if you switch off the video, the camera, then it will be better.
Yes. Okay. So today suddenly there is an urgent shutdown from the electricity board.
Okay.
So we are on kind of generator supply. So
Okay.
an issue. But anyhow, shall I start?
Yes, sir.
Right. So in case if I'm not audible, you can just have to interrupt me. I'm also seeing my WhatsApp in the side by side. So in case if that is locked, you can ping me there also.
No, sir. In case of any difficulties. Okay. Thank you, sir. Over to you.
Yeah. So I'll formally start. It's great and welcome to be part of FOSSEE, and I think I can never say no to FOSSEE. So that is what I have to share with all the participants who are there. Whatever small help that we can do to FOSSEE, I think it is great. To their initiative of bringing free and open source tools, one of which is OpenFOAM. I mean, free and open source tools, of which one of which is OpenFOAM with respect to CFD, for the benefit of faculty and students at large. So I'm part of, I'm happy to be associated, I think now about 10 plus years, right from Professor Kannan Moudgalya, what he has introduced. And that's what is my next slide. I don't want to wait till the end to give this gratitude. So my gratitude always to Professor Kannan Moudgalya. Then earlier I came with OpenFOAM with Professor Janani, and then it is Chandan Bose. And obviously all this happens through the communications we have with Payal Madam. And I could understand from the program schedule that there are a lot of volunteers, project managers, or the project engineers who are going to support this lab session: Nikhil, Manjil, Ivan, and Paris. And I had earlier worked, I mean, there were a lot of CFD summer fellows also, of which many are there. And I want to specifically thank Pranay, because there's a lot of things which we have learned from these people also, and obviously for the audience. The next I want to show is on, I have kept, this is a standard disclaimer slide, which I will always show as part of my presentation. I have two things to tell. One is on the image itself that you actually see here, that learning happens when one acts on oneself. It is not always from external. So external people can trigger the learning, but it all happens on how one person chisels themselves. And there could be certainly some mistakes, right, as part of my presentation, and sometimes it could be unnoticed. And I would urge the listeners, the attendees, the participants to go back and verify, and you should not take all the things that I say as always the truth. So you need to go back and then make sure that it is correct. And if you think anything is incorrect, feel free to write to me. My email ID, I think, is there in this first slide. It is prnarain@scbt.shastra.ac.in. And another thing is I have kept this presentation fairly simple enough, but not very simple, to an extent that you should appreciate. I understand this is a post-lunch session, and so I need to slowly pedal down and then make sure that you're geared up by the time food is also getting digested in your intestinal cavity. These are some of the references that I want to first tell, which help me to learn what is CFD at large, which could be of helpful to the community also, of which Dr. Ranade, I'm very, in particular, very gratitude, because he is also my PhD mentor or supervisor when I was there at NCL, Pune. So that's what I have for the slide part. And now I'm going to make it slightly more different in terms of the talk, because I understand that typically most online presentations happens in PPT and people get bored of. So I wanted to do it in the written mode, and I think off late, or rather after COVID, that has become my practice. Now, what I've done, at any time, you can unmute or you can put it in the chat box, and I think the FOSSEE volunteers will unmute and ask. So that's fine for me. And I'm assuming that my internet would be stable, but in case if it is unstable, I think again FOSSEE people can unmute and let me know, or the participants can put it in chat so that I can hear that ping sound and then go back and see in the Google Meet, because otherwise I do not be able to watch the Google Meet when I'm actually presenting, right? Now, what I'm going to do today is something I've captured here. We are going to see why we have to study first multi-phase flows, right? We need to have a shared understanding. I understand that there are 100 people here, so people could be of different learning backgrounds or domains. So we need to know something of what is multi-phase flow. Then we will see a little bit on multi-phase flow classification, then a little bit on equations and something called momentum exchange factor. And then I will lead you with an example, which I think is going to be taken by FOSSEE people in the lab session, which is on the bubble column. So I would show what is actually a bubble column is. Now, why multi-phase flows? So that means if we need to study or simulate multi-phase flows, can we try to understand that whether are we able to know what are these responses for ourselves? So that means, are we studying because we are very curious about it, or are we studying because there is a need to improve performance of an existing process? So typically any learning happens because of two reasons. Either it is we have observed something and we are curious to know why it is like that, or we require something. So that means there is a want or a need, and that need has to be better satisfied. Okay, when I say better satisfied, we want to produce more from less. So that means we want to decrease the energy consumption, but increase the product or increase its efficiency. So these two are predominantly the reasons why something has to be studied. Unless we are not convinced with these two, I think merely studying any aspect of knowledge will not be very fruitful. So a learner has to be first convinced with either of them. If both of them a learner knows, then it is just fantastic. But at least one thing the learner should know for sure before learning something. So let's try to do a small activity, maybe just 2-3 minutes. Can you think of any multi-phase flow system that you encounter in your daily life, preferably see it in a direct mode. I mean, I don't want to take any literature definition or the definitions from web or something else. Think of what you see from morning to night, and then see, is there any multi-phase flow in this? Okay. And if there is a multi-phase flow in that, then that means just see whether is that system, yeah, somebody has already started texting, is very good. Is that system is improved because of knowing multi-phase flow, or is it like something like curious or something like that? Think on that and you can put on the chat. Appreciate, I'm just seeing the chat also, right? Yeah, somebody has put river, air conditioner flow. If you are not able to think, you can just put this number 3 on the screen. So if you put number 3 on the screen, I am assuming that you are not able to understand what is multi-phase flow, or you are not sure whether multi-phase flow affects. Right. I'll just take 2 minutes and then I'll proceed further. It's not everything I have written down. I'm actually on a OneNote. It's not everything. I've just written some pointers and kept before this workshop so that I don't forget the leads, and the rest I want to make it live actually. Now I'll capture something that comes on the screen. So people have told about air conditioner, river, boiling of water, combustion, liquid, fuel, combustion, and then washing machine. The washing machine is more of a product. Now you have to slightly maybe refine what is multi-phase flow in this. All right, wood burning and so on. Okay, so I'll take with this. Now if I take this and try to put some leads, and so that you can take it, I mean, we can go further. Paint sprayer is a very good thing. Appreciate person who was put as a paint sprayer. Now, if you think of an air conditioner, the job is to actually cool the air in an ambient space, in our dining room or a bedroom or a hall or office room. But for that to do, it needs something as a refrigerant. It needs a refrigerant. And that refrigerant has to undergo between a liquid and a vapor space. It has to continuously exchange between a liquid and a vapor space. So that means there are 2 phases involved over here. And any performance of, obviously there is a compression, heat exchange and so on, but I'm just trying to pitch points on the multi-phase itself here, right? One is on the refrigerant, which exchanges between the liquid and the vapor space. Interestingly, I will take this again, paint sprayer. Now if you see that, that is actually a liquid, but that needs to be broken down to droplets, right? And then it needs to be sprayed also, or kind of abreast against a surface. But essentially the first process is on how this liquid can be broken down to droplets. The same thing happens for combustion also. In the engine part, the liquid has to be broken down into droplets. And why it needs to be broken down into droplets? If you have liquid like very continuous like this, if you think liquid is very continuous like this, and in this, suppose if you want to send, sorry, and if you, on this, if you want to send an oxygen and then do a combustion, against versus, suppose if I want to make this as small droplets, and then send oxygen and combustion, we know that the second process is better. The second process is better. Now, why is this better? Can somebody tell why is this better? So here it is a bulk. and it is here, it is droplets. Now, why this is better? The second one is better. Fantastic. More surface area per volume ratio. Exactly. So the process depends on this surface area, and because we have increased the contact area or the surface area, it is going to be now better. The process is going to be better. And this surface area, let me write as a letter A, right? If I write as a letter A, and I give the units as meter square by meter cube, which is we call as specific surface area. So which is nothing but surface area per volume of either we can say as a liquid, and sometimes we just take as a total system. So can you think of what this A depends on? This A is function of what? What governs this? What governs this contact area? This A bar, which I've written as meter square by meter cube in the SI unit system, what governs this contact area? Surface energy. Surface energy is required to make this area, but what governs that? I mean, if I change what, then this A will change. So that means if I need to increase this A bar, what should I do? That means which engineering parameters affect the A bar? That's the question. So somebody has put size, surface tension, phase change. But just think of this. If we decrease the size, the surface area will increase. But are we controlling the size? Are we decreasing the size in the process, like say fuel combustion or paint spray, right? Or many other things also for that matter. Pressure difference. So I assume that you have started now thinking. That's all I want. Is it clear? So it's a kind of a free flow introduction to the multi-phase flow. So all we understand is what makes this A. I mean, what makes this A? That is the curiosity question. But then the other question is, what can I do to increase this surface area, right? So you can see this could be, first one is more scientifically driven. The second one is more of an engineering question, right? And if we need to find answer for this, if we want to make a better sprayer or a better combustion system, then we need to understand multi-phase flows. And that comes the motivation part, right? So I hope the learning that we have in the last 5-10 minutes is the motivation for multi-phase flows, right? I hope this should be clear now. I'll just move ahead. I'll just skip something and I'll just go. This is one reference. I will put this also through Payal Madam, or you can just later on take it down. You don't need to now see this reference, but go back and please read this reference if you want to understand how process modeling itself, not just CFD, is of paramount importance even now, right? It has been there for the last, I think, 50 years. But if we want something very sustainable, then we need to go back and then see CFD sits here. CFD is somewhere here. All this is what is about CFD. There are many things other than CFD also. It is given, like, for example, we do have Aspen ICs, which is a different kind of model. But you go back and see this spectacular review by Professor Nanda Kumar and Professor J.B. Joshi, and KDP Nigam. KDP Nigam is actually a chemical reaction engineer from IIT Delhi, and you would love it. So I'll skip and then go. Okay, so if you want to understand multi-phase flow, how are the multi-phase flows classified. So any idea on that? On what basis are they classified? One is on the number of phases. So we are classifying the multi-phase flows as 2-phase, 3-phase flows based on number of phases and what phases are there. What do you mean by what phases? Suppose if it is liquid, gas, and solid. Now we can think of, we can have a liquid solid or a gas liquid, liquid liquid, liquid solid, gas liquid, gas solid. Then we have gas liquid liquid, gas liquid solid, so forth. So you can have either 2-phase flows. So these are 2 phases, whereas these are all 3-phase flows. So based on this flow and based on what phases are there, they are classified. But there's little more other ways of classifying is based on something called dense and dilute phase flows. And that depends on, flow regimes. And that depends on, I'll come back to the flow regimes. I think that's from Mayank. It's very nice. What are dense and dilute phase flows? It tells on, like, suppose if you have a system, right? Consider 2 system. This is 1 phase. Okay. This could be a gas bubble or a liquid droplet, which is actually is there in another liquid like this. So I'm asking you to compare this. I'm just drawing 2 such images. Now in 1 and 2, which is more dense? So it is very intuitive, right? I think people have already started responding 2. Now, how did you say 2? You are only seeing it. What your brain did to say that it is 2? Obviously, this is dense and this is dilute. So what did your brain do? On observing this image, something your brain calculated instantly. Right? What did it do? Right? More solid fraction, yes. That's a very good technical word, and it is actually right. But what was your brain trying to do? What quantification did the more circles? Fantastic. So the brain was actually trying to find out how many circles are there, right, on a vis-a-vis comparison basis, right? Now, from these circles, we need to move to a more technical term that we will later on use it, right? More interfaces, fantastic. More interfaces, more circle, but more interfaces related to area performance that we spoke about. But when I say dense, you are talking about more circles, but we are also talking about 2 other terms which helps in this definition, right? One is called phase holdup, and another is something to do with the mean free path. Okay. Mean free path. Holdup is defined as volume occupied by a particular phase to the total volume. So this is volume of, like, say, phase 1. In this case, whatever is written in that violet color circle divided by the total volume. So which is nothing but the volume of the circle plus the volume of whatever was drawn in the blue color. Is it clear? So this ratio is usually given a letter epsilon, volume of the phase divided by the total volume. And this helps in classifying whether something is dense or dilute. But when something is dense, what is the consequence of being dense? If it is so dense, what happens because of that? What is the consequence of that? That consequence is something to do with this mean free path. if the system is more dense, if the system is having more of one phase when compared to another phase, what happens is there is some more interaction between these phases rather than between the phase and the between that phase and another phase, right? So that means if you have two phases, phase A and phase B, if your holdup of phase A is much larger, okay, if it is much larger than 1, this ratio will be always between 0 to 1 because it's a ratio of one phase to another. If this is much greater than 0, I mean, sorry, it is about not greater than 1, sorry, it is much greater than 0, that means it is order of close to 1. If it is order of close to 1, then interaction between A and A will become predominant, right? Interaction between A and A will become predominant, right? That does not mean this number is 0.9. Can you guess what is this number if A interaction has to be predominant? From experiments, from modeling, this number is hardly 10%. So that means if the holdup is of the order of 0.1, if the order of 10%, yes, fantastic, then that is something we classify as dense flows. Now, if there are dense flows, so that means we need to do something in modeling. But at this page, I just want to stop on classification. So we can classify based on dense and dilute, based on whether the holdup of that particular phase is more or less, right? Then obviously we have a classification, something called primary and secondary phase. This is quite easy to understand. Primary phase is the one that completely fills the domain. The secondary phase is usually the dispersed phase, the one that is discrete. Now, in this picture, you don't see these violet circles everywhere. So violet is actually the secondary phase or the dispersed phase or the discrete phase. But everywhere the blue color phase, right, is actually there. So that is actually called the primary phase. Now, apart from this definition, there are also other ways of classifying based on the equipment itself, right? Now, if you have a column like this, okay, which is like filled with a liquid, it need not be water, it is just filled with a liquid. And if you sparge a gas, this gas can form droplets. This is called a bubble column, right? Now, it can be just a single bubble or it can be a group of bubbles. So this is something called bubble column. Like this, we have something called stirred tank. Now, a stirred tank is something like you have a slightly broader vessel, a cylindrical vessel, which will have an impeller and that is stirred. Now, one phase could be there and a second phase could be sparged from bottom. This is something to do as a stirred tank. Now, we also have, this is in terms of gas liquid, but we also have something in terms of gas solid. Now, if you take this column, right, you close at the top and the bottom, right, with a support, right, and then make it filled with a solid, right, and then you can sprinkle fluid from the top or from the bottom, right, or sparge gas from the top or bottom. These are typically called as fixed bed system. These are fixed bed system, or more commonly called as trickle bed. Now, this trickle bed are essentially the trickle bed are essentially liquid solid, gas liquid solid systems, right? You can have two phase or you can have just three phase also. And the liquid can be co-current, counter-current, upflow, downflow. So that means it can be co-current, it can be counter-current, right? So in this case, it is downflow liquid solid system. But if I introduce gas also sparged here, then it is like it will become counter current because liquid is coming down and the gas is actually going up, right? So this could be something like this. So this is one another way of classifying. So all you can see is there are different ways of classifying. But let's go back to the question and connect with what somebody texted a little before, right? If I take the same system, if I take the same two-phase system, okay, in the same contactor, so that means in the same emitter, do they have same flow structure? Do they, that means, do they look same? What's your answer? So that means if I say that I have a contactor like this, it's a cylindrical, suppose, vessel. If I fill this with liquid, right? And if I sparge gas into this, right? Do you think that it will always look similar or same? Do they always look similar or same? This is connected to something what somebody texted before as flow regime. They actually do not look same. They actually do not, may not be always same. Exactly. So this is something like what is called the flow regime. It could be the same chemical substance. So that means it is same liquid, same gas. It could be water and it could be just oxygen that you are sparging. It could be in the same contactor. So that means you are not changing the equipment, you are not changing the liquid, you are not changing the gas. But how this gas and liquid contact with one another might change. So that means it is not only the properties, it is not only the equipment, it also depends on something else. Now, what could be the something else? That something else is the operating condition. So that means the flow rate or the velocity, right, of both the phases. In that cases could be not only the primary phase, but it could be the primary phase or the secondary phase will govern the local pattern. This flow pattern, if we do not understand this flow pattern, then that means we will not be able to capture the performance, right? Because this flow pattern essentially controls the holdup, and the phase holdup eventually controls the surface area, like what we saw earlier. So that brings back to our question. So maybe I'll just see whether I can just show this. Just a minute. Yeah. In the slide, are you seeing the flow image? I think I'm getting slightly lost in the net. Are you seeing an image? No? Yes?
Yes, sir.
Yes. Okay. So this is again in a reference. I will share the reference later on. Now you can see that in the horizontal flows, be it vertical flows, there are different contacting patterns that will happen based on how two fluids are introduced or what is the velocity of the flow rate with which the two fluids are introduced. So it is not the same. So that means if we don't understand this, if we don't predict this, then we cannot get better performance. So that means if we want better performance, then that means we need to be able to predict it. If we don't predict these, then we are not going to improve the performance of whatever the process that we are talking of. So that is where lands at to how to model these multi-phase flows. There are three approaches in modeling. One is called WOF, volume of fluid. Another is called two-fluid model. So the two-fluid model is also called Eulerian model. And the third one is the Eulerian Lagrangian or the dispersed flow model. Now, it is not which model is better and which is good. It depends on what are you looking into in all this model. I mean, what is your output that you want? When we do, I mean, if we are interested in the shape, so that means in the surface of the secondary phase, like when a bubble is introduced, you want to see actually the shape of the bubble. You want to see the actual shape of the bubble and predict how it bends and everything. That is where we do WOF. It is not only for a gas bubble, it could be for a liquid droplet, or let's say, suppose if the solid particles are being put and you want to see how the solid particles gets arranged, then we do WOF. We do two fluid model. If we are interested in this holdup, we want to know how much of one phase has percolated the another phase. In a same system, how much of one phase is there in another? If that is what is our interest, if our interest is in this area, surface area per unit volume that we spoke, then we typically do in Eulerian model or the two fluid model, right? It is called as two fluid model, but that does not mean you cannot use it for gas liquid system. When you use it for gas liquid system, we don't tend to call it as a three fluid model. We generally call it as an Eulerian model. That's all. The last one is actually the dispersed phase. If we want to track the motion, of a or a few set of secondary particles, or I mean the dispersed phase particles, entities. So the dispersed phase entities, then we do it. Then we do actually the EL model. So the question comes, are we interested in shape? Are we interested in the holdup or the area? Or are we interested in motion? So that means you cannot do one and then get everything else. So there is no one model which does everything else. So it depends on what is expected in that. There are broadly three approaches within the RANS approach. Now, I'm not here spending time what is the general governing equation of CFD and RANS and everything else. I'm assuming that a fair amount of introduction was given in the previous session, or otherwise you can go back and see. I once again reiterate, the idea of this 1 hour session is not to make somebody an expert. I don't think anybody can make anybody expert in just 1 hour of any particular field of knowledge. Forget about CFD, multiphase, and everything else. So I'm just giving pointers so that if this is something interesting to you, you will take leads and then go back and then do it. Now let's jump to, we have about, I think, 20 minutes. We'll just see what are the equations specifically with respect to Eulerian, and we'll see some key terms that govern the modeling of Eulerian. Right? Now, what is a law that based on which the CFD is governed? That's very simple, a fairly straightforward question. The law is the law of continuity. So the one which for the conservation of mass and obviously the conservation of momentum. So which is called the Navier-Stokes equation. If you are doing thermal energy balance, then we also have law of conservation of energy. So if you ask laws, there are laws are only three. One is the continuity equation, which is based for mass conservation. Then we have the Navier-Stokes NS equation, which is actually for the momentum. And then we have the energy balance, which is law of conservation of energy, which essentially comes from thermodynamics, right? Now, I'll quickly go back and tell you how was your equation for a single phase that you did and how it can be easily extended or viewable for an Eulerian or two-phase system. Your equation has 4 parts, right? One is actually the accumulation term or the unsteady term. Then we had the net outflow, which is actually called the advective term or the convective term, and that was equated to the net outflow, but due to diffusion, due to the molecular process, and then all source and sink. So the equation essentially has just 4 parts: an accumulation or an unsteady term, an advective term or a convective term. So that means this because of the bulk motion, and then we have the diffusion term, which is because of the molecular motion, right? And then a source or a sink. These are the 4 parts. I hope you will be able to relate your Navier-Stokes equation with these 4 terms. Now, for example, if I write it for one direction, for let's say the x momentum, the Navier-Stokes equation might look something like this: dou by dou t of rho u, so which is actually the accumulation of the x momentum plus the gradient of the momentum, that is can be in all the direction. How x momentum gets transferred in all the directions, that is what I have written as the next term. And then the shear stress term, which is actually the shear stress term, how the shear stress itself gets distributed in again all the directions. So you have the gradient of the shear stress that would be written in all the term. And for the source term, we usually have the pressure, right? Because the flow happens because of pressure. This is what essentially the Navier-Stokes equation for a single phase flows. If you can just duplicate this, right? If you can just duplicate this for 2 phases, that becomes essentially the Eulerian or the 2-fluid model. That's all essence, right? But you cannot directly write this equation for twice. It is not about writing this equation for twice. It is writing this equation one term for every phase. So that means you have to, if there are 2 phases, you have to write this once for both the phases. So that is what I mean. It's not just simple duplication. So when we duplicate, right, we need to tell it is the density of the primary phase or the density of the secondary phase. So that means I don't write dou by dou t of rho into u. I write it is the density of the primary phase times the velocity of the primary phase, right? So suppose if I write it for a gas liquid system, let me specifically write for the gas liquid system, I will write rho L UL. So that means where it means that I'm writing for the density of the liquid and the velocity of the liquid. Plus, again, the convective term. The convective term is again based on the density of the liquid and the velocity vector of this liquid. Velocity vector of this liquid going to all other directions. So that means again one more the divergence of that. Then the shear stress. The shear stress again because of what is there in the liquid phase plus a pressure force. Let's say suppose if I write this equation like this, there's something still missing in this equation. What is missing in this equation? We are not told how much is the liquid is there in the system. So we need to include something like the fraction of the liquid in the system. Every term should have a fraction of the liquid that is there in the system. So that means every term will be accounted or factored for epsilon L. Now, what is epsilon L? Epsilon L is the volume occupied by the liquid to the total volume. So if you have a gas liquid system, it is volume of the liquid by volume of gas plus volume of liquid. So that is what is epsilon S, right? Yeah. But is this still complete? If you ask if this is complete, no, this equation is not yet complete. Something is missing. No, we may write this equation one more time for gas. Let's say, suppose if I write this equation again with the term now epsilon G, making everything is now for a gas. If I write this for a gas, I'll write pressure term for the gas. I can write 2 times. But still that will not solve for the multi-phase flow. It is still not something not done. Why it is not done? Now, if you can think why it is not done, how are these two equations connected? Is there any connect between these two equations? Is there anything that mathematically connects these two equations? Obviously, you may say that this hold up is a connection term. I agree. Hold up is a connection term because if the liquid hold up is 0.6, the gas hold up is 0.4. But that only connects for the presence. It does not connect anything for the motion. So we need to connect something for the motion, and that gives that missing term that we need to have something called exchange coefficient, or which is called interface exchange coefficient. So this interface exchange coefficient between gas and liquid, right? They are opposite to one another. So if I say liquid is pushing the gas, then the gas is getting pushed by the liquid. So they are one and the same, right? If the liquid is acting, if the liquid force we say as positive from the liquid size, then from the gas side it is just negative because it is just being acted upon. That's all, right? So only pressure and shear does not complete the picture. We need something called this interaction term, and that comes to the last maybe 5-10 minutes. What are these interactions between the two phases? How are these interactions captured? Now, in multi-phase flows, this interaction force between a primary and a secondary force is captured in terms of a coefficient of interaction and the relative velocity. So there are two terms, or which is called the slip velocity. So I have put P and S. P and S stands for the primary phase and the secondary phase, and K, what I've written, is actually the coefficient of interaction and the slip. Now, what do you mean by slip? The slip is a difference in velocity between the primary phase and the secondary phase. Okay. So the slip essentially gives the direction based on the motion, and there's a coefficient. Now, this coefficient is not a constant. This coefficient itself is actually a function of velocity, but this interaction forces can be classified again. There are many other forces, but predominantly you need to know something about drag force, lift force, and virtual mass force, right? There are many other forces. There are something called history forces or Bassett forces and so on and so forth. But I'm just saying that we need to think of about 3 at least forces. Drag force is because of one phase moves through another. Whenever a system moves through another phase, through another system, then there is going to be a drag. You can never avoid a drag. Drag is the reason why you can think of the second law of motion. What you say is U is equal to V is equal to U plus AT that we have studied. If you drop an iron ball, if you think of dropping an iron ball and let's say a feather from a huge height, let's say if I think you're falling from 10 meters, do you think this iron ball and feather will reach the ground at the same time? They don't reach at the same time. The ball actually reaches first. Maybe it will just reach in 2 seconds, whereas this might take 5 minutes. This difference actually comes because there is a drag, because this particle moves through a fluid. So whenever a system is moving through another system, we have something called a drag force. The lift force is also essentially the same. Only thing is the component varies. One is in the perpendicular component and another is in parallel to that. So these two forces are actually perpendicular to one another. Now, what is virtual mass force? Virtual mass force is because suppose if you have a liquid droplet, right? Now, this liquid droplet can actually carry some amount of gas with it, because as the liquid droplet is falling, it can also trap the gas into it. A gas bubble can also trap liquid when it moves through. So that means it can give an artifact of a different mass for that. That is actually called the virtual mass force. So these three forces have to be modeled if we need to capture, if we need to capture the Eulerian or essentially the holdup, right? So I understand that it is slightly now going tougher, but I will just try to summarize something like this. We, in an Eulerian model, we are modeling both the phases, the primary and secondary phases, as two fluids. So that means two times, but they can talk with one another. What do you mean by they can talk with one another? That means they know the presence of each other. And how they know the presence of each other? They know the presence of each other by something called holdup and something called the interaction forces. So this interaction forces has to be modeled if we need to capture this holdup. And this holdup is what is predicted at the end of simulation. I'm not going to take too much time to explain bubble column, but just want to give a prelude so that it is easier for you in the lab session. Now let's take that we have a long column like this. Maybe this is like, say, 1 meter. This is not 1 meter. This could be like, say, 25 centimeter cylindrical column. Now you can think of a 2D or you can think of a 3D. Let's say it is filled with a liquid and you are leaving a single bubble at the bottom. Okay, single bubble at the bottom. Can you capture how this bubble moves on? Can you capture how this bubble moves on? That is one aspect. Instead of single bubble, if you just leave a range, an array of bubbles, what happens? I think this is something that you are going to see as part of the lab session. I don't want to take much time here and then yeah. So maybe I think we can stop here. Is that fine?
Yes, sir.
Yeah. So essentially you will play around and then try to get some hands-on experience on how is that simulating and everything else. Eulerian and Eulerian Lagrangian, all those things, if you don't understand now, it's all fair and good. All you have to understand is put two faces, right? You have to use two faces and connect them. What do you mean by connecting them? Is like kind of interaction between them. And you need not worry whether you are using WAF or Eulerian or Lagrangian at this stage as a beginner. Just play around, get a feel of how this motion can be captured. With this, I once again thank all the FOSSEE team members for nurturing this Shastra FOSSEE club, and we are immensely blessed. If there are any of the faculty members who are interested, I think you should talk to Payal madam and then take up FOSSEE club activities as part of your institution also. Instead of saying that I did this CFD, I learned that CFD or Eulerian and something like that, what is the best proof for a student to show that he or her has learned CFD? Is simple. Submit a case study. And if you submit a case study, I think Payal might talk on this towards the end of the workshop. It will be hosted in the IIT Bombay server. And I think when your student just goes to any interview or any admission, if they just give that link, that testimonies that somebody has indeed learned. So I would welcome all the faculty partners to take the initiatives and let us give it back to the students henceforth. Thank you. Thank you, Payal madam, and thank you, FOSSEE team. Yeah, Payal madam, you can take on. Yeah, Paris is there.
Yes, sir.
Yes, Paris and even both are there.
Sir, there are some
There are
questions.
questions right on the chat box. I was
Yes.
just
I'm just seeing the chat box.
I'll tell you the question. What is the role of surface tension if there is multi-phase flow?
Okay, if you are using the WOF model, so in the Eulerian model or in the Lagrangian model, it is not very direct. You won't be able to see directly as a term, but nevertheless, that this effect of surface tension is incorporated in other coefficients, how the empirical relations were derived. But if you're doing the WOF model, there is a direct influence because the surface curvature that we need to get. So if it is going to be a droplet, how the surface needs to be drawn, that is actually based on the surface tension force, how it is resolved locally. So in the WOF model, in short, yes, the surface tension captures the shape. In the Eulerian and Lagrangian, you don't see this directly. The next question.
No, sir. As of now, there are no questions on YouTube.
Okay.
People are typing it.
Which model should I use to capture hemodynamics in artery? See, if you are interested to capture, I understand that you are going to do on a biological flow. So you may actually try it as a single phase flow, but with non-Newtonian. Because when you're talking about hemodynamics in artery, you want to know, in a sense, do you want to make the walls flexible? That is one question. But if you want to not make the walls flexible, because the artery wall is not rigid wall, it actually flexes. The cross dimensions can change. If that is not your intention, if your intention is to see how the blood flows or the plasma flows, and you want to capture the interaction between the plasma and the WBC and the RBC, then you need to model as multiphase. But if you only want to know their pressure drop or the mixing characteristics, then you can approximate blood as a single phase flow, but it is no longer a Newtonian. You need to put an appropriate non-Newtonian character and then try to simulate it. I think this is to Professor Iqbal. The complaint wall. So if the wall is actually changing, we cannot directly do that. We have something called moving reference frame. So through the moving reference frame, we can give actually the motion to the wall, to the boundary of the wall, and then simulate it. So that is possible. Yeah. Anything else?
Mr. Arpit Dwivedi has raised his hand. If he has, he can directly ask to sir.
Yes. Okay then. Yeah. Thanks to all of you, and I hope you will have a good workshop session for the remaining days. Thank you, madam.
Yeah, thank you so much, Professor Naren. Thanks a lot. Paris, was there any more question? Actually, sir, just a second. Mr. Arpit Dwivedi had raised his hand. So, Professor, or I don't know, Mr. Arpit, do you have any questions for Professor Naren? You can unmute yourself and talk. Otherwise, you can also type on the chat box. I don't know. I think it was my mistake, maybe.
Okay. Yeah, no issues. Yeah.
Okay. Thank you so much, Professor Naren. So, yeah, I have. Okay, just a second. So, Mr. Arpit has a question. I think he's taking some time to type it.
Okay.
Okay, so Deepak, could you please do something from the settings so that Mr. Arpit can unmute himself and talk?
I have given the permission.
Okay, so Mr. Arpit, please try unmuting yourself now.
Arpit sir is already unmuted, ma'am. Maybe we are not able to.
I can see that. Maybe he has some audio issues from his side.
Yeah, so you can ask him to write to me. I will.
He is typing.
My email ID. So if I know the answer, I will respond. If I do not know the answer, also I will respond. I'll say I do not know the answer.
Sure, sir.
Yes. Thank you. Thank you, madam. Yeah.
Okay. So Professor Naren has given his email ID. Probably you can also directly email him and ask. Otherwise, you can also email us at contact CFD. Then we'll coordinate and get back to you with the answer.
Yeah.
Okay, thank you so much. So Professor Naren is an executive faculty partner with FOSSEE CFD team, and every year he is guiding a lot of students. He's taking these kind of lecture sessions in our workshops, faculty development programs, and we are really thankful and grateful to Professor Naren for his contributions towards FOSSEE. So thank you so much, sir, for joining today.
Thank you, madam. Yeah, I'll take lead.
Thank
Sure,
you.
sir. Thank you so much.
Thank you.
Nikhil, I think you are ready for the hands-on session.
Yes, ma'am.
Okay. So Nikhil Chidnavis is from FOSSEE CFD team. So today in this session, he will be the resource person who will interact with you and present you the demonstration session and the hands-on learning activity. So over to you, Nikhil.
Should I start, ma'am?
Yes, you can start.
Okay. So good afternoon to all. I am Nikhil Chitnavis, research associate in FOSSEE team. So after a very informative lecture from Professor Naren, I'm going to give the hands-on session on multi-phase flow, starting with the bubble rising using the VF model. And if the time permits, I will also show how to model the bubble column, which Professor Naren was talking about. Whether the screen is visible?
Yes, sir.
Okay. Yeah, and the presentation also.
Yes, sir.
Yeah. Now
it is visible, sir. It is visible.
And it is changing also?
Yes.
Okay, thank you. Yeah. So we'll start with two-phase flow model. Anyhow, Professor Naren has given a very good introduction about multi-phase flows, starting with the continuous flow model. So in continuous flow model, as he described, our intention is to track the interface of the two continuous phase. There are various examples for continuous interaction between two phases, like wave motion, free surface flows, even the rising of a single bubble inside a continuous medium, in which we can track the interface of the bubble. So we'll start with that problem itself. In which we are going to use the volume of fluid model to track the bubble interface, for which this problem I'm taking. So in this problem, the dynamics of the gas bubble we're going to see in the static fluid column, where the one phase is trapped inside the other phase. So it's a water and air interaction, we can say that. And the numerical simulation has been performed, and the interface is tracked using volume of fluid model. So this will be a 2D case, and I think Paris has already shared the drive link. Let me show you where it is. So in day 2, inside this multi-phase flows, so this rising bubble new folder is there. Please download this. And this will going to see how the bubble will interact with the continuous phase. So once everyone will be ready, I will start the hands-on session. Okay. So it seems like most of you have already downloaded. Jitendra sir, can you please clarify what exactly you are referring to? Okay. So which I was referring to. So this blue bubble,
Nikhil, sir.
yeah.
Sorry to interrupt you. I guess sir is Jitendra sir is asking about the drive.
Oh, okay, fine. So in this FDP, which was earlier shared by Paris, inside this day2 folder is there in this multi-phase flows. And please download this rising bubble underscore new. Is it fine, sir? Okay, fine. Unable to download. Can you please check this, Paris? Why?
Yes, Nikhil sir, you can continue.
Okay, fine.
They're in chat. So.
Okay. So this case is something like this red color is the continuous liquid phase, and inside this blue color bubble is there, which is the air or some lighter phase, which is trapped inside this continuous phase. And over the period of time, how the bubble will going to rise inside this continuous phase, we're going to see. And we'll start with going through the case structure, starting with zero folder, constant folder, and system folder, how to set up the test case for such kind of multi-phase flows, where we're going to track the bubble interface or any interface. And also, the case structure will be different for OpenFOAM 2412 and OpenFOAM origin.com version. So one by one, I will going to explain for both the OpenFOAM version. So I will start with OpenFOAM 2412. I'm using 2412 version. And later on, I will explain for OpenFOAM 9, 11, or 13 version. So this is the case structure in which if we'll start with zero folder. So in zero folder, as we all know that we're going to set up the boundary condition and all the parameters. So apart from velocity, that is U, and PRGH, that is pressure. Now one more file you will able to see, which is alpha phase. So in the Naren sir's lecture, he was referring the volume fraction by a symbol of epsilon. Instead of epsilon, I'm using alpha. And it will be better if you delete this alpha phase 1 file, and we're going to create it again. I hope the fonts are visible.
Yes.
Yeah, fine. So we'll start with 0. So as I've said, one phase is trapped inside the other. So that means we don't have to give any additional velocity or any other boundary condition. So that's why these are 4 walls. So these are 3 walls, and this is the outlet. So that means when the bubble will reach this boundary, it will escape from this continuous domain. And these are 3 walls. So walls means we have to give the no slip boundary condition on these 3 walls, that is left, right, and bottom wall. So same boundary condition I have given. So if you see, either you can define the boundary condition type as no slip or the fixed velocity of 0. Both are fine. So for these 3 walls, I have defined the no slip boundary condition, and for the top wall, I have defined the inlet outlet pressure. That means once the bubble will reach to that point, it will simply escape. So no slip boundary condition means I have simply defined the fixed velocity to 0. So it's a fixed boundary condition. Based on velocity, the pressure has to be, the pressure has to be given a 0 gradient boundary condition. So that's why on this 3 wall where I have defined the no slip or 0 velocity, I have given 0 gradient for the pressure, and at the top wall, I've simply defined the pressure to be 0. Now coming to the alpha phase. So if you see, as of now, I've simply defined 0 gradient everywhere. That means the field is not yet set. So nothing. If you open the file now in ParaView, you will not able to visualize anything. So to visualize the bubble trapped inside the continuous phase, we have to set some fields. So that field is given in system folder. So if you open the system folder and this set fields, let me show you in ParaView also. So this is the domain, and which is given a 1 cell thick, which is having the thickness of 1 cell, and we are solving it for 2D, and that means front and back has given empty. So now if I'll so if I open this alpha phase, you can see everywhere it is 0. So why is it so? Because here, if you see in alpha phase, I've defined the internal field as 0. So how to set or how to visualize the continuous field, that is liquid, and the bubble? So for that, we'll go to the set field dict file or set field dictionary. Here we'll go to define in that whole domain which part will be the continuous phase and which part will be the trapped phase or the bubble phase. So you can see, first I have defined the default field. So default field means all over the domain it will going to set a default phase. So we have to be clear with the numbering of the phase. So if the alpha phase 1 is given the value of 1, it will only have a 2 values, 0 and 1, for this VOF model. So if the alpha phase is having the value of 1, that means it's a liquid phase. And if it is having a value of 0, that means it's a bubble phase or secondary phase. So by default, I have given the volume scalar field value everywhere in the fluid domain as 1. Now inside this continuous phase, we have to define a bubble trapped inside this continuous phase. So for this, there is one option called a cylinder to cell. That means we're going to, so it's a 2D geometry. So how to define a circle inside that 2D geometry? That's why I have taken a cylinder. So anyhow, in the Z direction, how much thickness you are giving it to the cylinder, or whatever the length you are giving it to the cylinder, it won't matter. It will shown to you as a circle. So that's why it's a cylinder to cell. So first we will define the point in the front and back plane. So that means these are the two planes. So these are the two planes. We're going to define the point on these two planes. So that's why it is 0.5, 0.5, and 10 to minus 10. As I said, whatever the length you can define it in the Z direction, it will not going to affect. So these are the 2 points. And this is the radius of that trapped phase. And now I have to define what is its field value. So that's why I have defined the volume scalar field alpha phase as 0. So this is going to initiate that trapped phase, and we'll able to visualize it. Now, in the constant, as we have seen, all the phase properties we have to define, or all the fluid properties we have to define. So in the multi-phase flow, if you go inside the constant, so first we'll see for the dot conversion, that is OpenFOAM 2412 or whatever version we are using, starting with 2206, 2212 in that series, dot conversion, not for OpenFOAM 9, 11 or 13. So first I will show how to set up the test case for OpenFOAM. I'm using 2412. So for which you will going to use these three files: G, transport properties, and turbulence properties. And yeah, this much only. So one by one, we're going to see what we have defined in these files. So as it's a multi-phase flow, so gravity will come into effect. And as it's a 2D domain, so gravity will act in the y direction. You can, based on the application also, you can change the direction, or based on the orientation of the geometry, you can change the direction of the gravity. But for this case, we are taking the gravity in the y direction with the value of 9.81. Now, turbulence properties means what kind of flow simulation we are considering it. So for this, it's simply a single bubble rising inside a fluid domain. So we are taking it as a laminar simulation. Now coming to the transport properties. So here we have to define how many phases are there. So there can be 2 phases or more than 2 phases also. So that we have to define. But in this case, we are simply taking 2 phases. So that's why we have defined the phases as phase 1 and phase 2. Now, the properties of both the phases we have to define. So the transport model, that means what kind of fluid it is, that we have defined for both the phases, as it's a Newtonian fluid. And you can change the kinematic viscosity and density of both the phases as per the convenience. But I have taken these values so that we can clearly see how as it's a very viscous fluid, so that we can clearly see the interface of the bubble in the continuous phase. So I have taken the kinematic viscosity of 0.01 and density of 1000. So this is a continuous phase, and the bubble trapped inside this continuous phase should have the density lesser than the continuous phase. So that's why the phase 2, I've kept the kinematic viscosity equivalent to the phase 1, but the density is lower than the continuous phase. Now, as we are tracking the interface, so surface tension will also play a very crucial role. How properly it will going to capture it. So this sigma is the surface tension, keeping the surface tension of 24.5. So we are taking a very viscous fluid. It is not water and air. You can try later on using the property of water and air and the surface tension of water and how the bubble behaves inside that kind of interaction. And coming to system, so I've already explained this set field file. Now we're going to see this remaining 3 files. Yeah. So in the previous section also, Ivan and Paris has explained what control or control dictionary has its function. So in this, we will going to define, we have defined from where the simulation will going to start, what will be the end time, what will be the delta t, because it's a transient simulation. Then at what interval we're going to save the files. So this is the right interval. So after every 0.01 second, it will be to save one file. We are writing all the file in the ASCII format. And because we are taking the adjustable runtime, so that's why we have defined the maximum value of coordinate number, maximum value of alpha coordinate number, and maximum delta t. So by defining maximum delta t, it will not going to cross the delta t of 0.1 all over the simulation. Coming to the discretization scheme, so the time variable we are discretized using Eulerian method, and all other using Gauss linear second order scheme. Even the convective term, which is defined in this divergence scheme, here also we are using second order schemes, second order upwind scheme for velocity and even for alpha phase. Even the pressure we are, this Laplacian term is the pressure term. Even this also we are discretized using Gauss linear second order scheme. Now, once the Navier-Stokes equation is discretized, it will going to solve over the domain, and for that it will going to form a matrix. So this matrix solver, we defined it in FE solution. So apart from pressure and velocity, which for which we are using Gauss-Seidel method, one more variable will come into effect now, which is alpha phase. And this will going to solve using, it's a variant of Gauss-Seidel only. So here we will going, here we have defined the matrix solver for pressure, velocity, and volume fraction, that is alpha. And this solver for the multiphase is based on Pimple form. So that's why these other parameters we have defined, that is n outer corrector, n corrector, and n orthogonal corrector. So these are nothing but the number of loops for the convergence we are defining. You can keep it as 0 also, but if the solution is diverging, you can play with these characters, that how many number of loops you wanted, so that over the period of time, the solution will get converged. So first we'll go going to see for OpenFOAM 2412. I will initialize OpenFOAM 2412. I hope the fonts are visible to everyone. So the mesh I have created using block mesh. It will be better if I'll show the block mesh also. So I've already created the mesh. We'll delete it and show it from the scratch. So as I've showed, this is the dimension of the geometry. Width is 1 meter, length is or height is 2 meter, and at the point at the location of 0.5 cross 0.5, the bubble is located. So the center of the bubble is located at the coordinate of 0.5 comma 0.5. So this we have already defined in set field dictionary, and the mesh I have defined it here. So all the vertices I have defined it here. So width is 1 and height is 2, and z direction I have simply taken as 0.1. And anyhow, it is a simple rectangular domain, so only one block will be there. And all the patches I have defined it here, starting with top, bottom, left, right, and front and back I have defined as empty. So to create a block, or to create a mesh, I'm using block mesh command. And it is a good practice that after creation of every mesh, you run this check mesh command, just to check what is the non-orthogonality. So as it's a rectangular domain, So all the mesh elements or all the lines in X and Y direction will intersect with each other at a 90 degree. So that's why there will be no non-orthogonality. Skewness will be also very minimum or almost equivalent to 0. And the total number of cell it has created is 12,800. So once the mesh is created and after checking the mesh quality, so we're going to run this command set fields. So as I've showed that before running this set field, there is nothing inside the fluid domain. If you click on this alpha, you will not able to see anything. But once or after running this set field command, just write this set fields and press enter. So now you can see that it has set the default phase, that is 1, and whatever the point or radius we have defined for the second phase, it is taken that so with the phase value of 0. Now if I'll refresh the para view, now this alpha dot phase 1 is coming. So now if you'll see, the continuous phase of phase is also visible and the bubble is also visible to you. So till here, I think everything is clear. Yeah, fine. So we'll move forward. So till here we have seen how to set up the test case for this rising bubble case. So we are using interform as a solver. So we'll simply type this interform and we'll not go into the detail of this interform. I can show you what all the running equation it is solving. So whenever in the multi-phase flows we are solving the, or we want to capture the interface. So in any flow problem, we're going to solve the continuity equation. This is the momentum equation, and this is the source term where this sigma denotes the surface tension. So when you are seeing these two equations, it is same as what we are solving for the single phase flow. The additional equation what we are going to solve to capture the interface is this alpha equation or the volume fraction equation. So this alpha denotes the volume fraction, or you can call it as epsilon or alpha, whatever. So this, by solving this equation, we're going to see the interface of any dispersed fluid. In this case, it's a bubble, or whenever it is a droplet case, so liquid will have the interface and continuous phase will be the air. So to capture the interface, this convective term need to be discretized. So for discretization, there are various discretization schemes to discretize this convective term present in the volume fraction equation. So one of such discretization scheme is PLIC, which is piecewise linear interface calculation. So these are the main equations which this interform solver will going to solve to capture the interface and to see the dynamics of the bubble. So this is the interform solver. So after pressing enter, so as it's a 2D domain and the total mesh element is only 12,000, so it will not going to take much time to run. and we'll able to see the dynamics of the bubble and nice animation. So I will only run it for the time of 2 seconds, and then I will stop. So now you can see, as I've showed in the control dict file, that after every 0.01 second, it will going to store one file, or it will going to save one file. So you can see after every after every 0.01 second, it has saved one file, starting from 0.01 and carrying. So now we'll see the animation as we have saved a lot of files till the end time of 2.09 second. So simply refresh it. Now you can see the total frames is also visible here. Now once we'll start to play, you can see the bubble is rising inside the fluid domain, and its shape is started to deform. Now, as I've said, that the top wall I have given the zero pressure boundary condition. So once the bubble has reached to this patch, it is slowly escaped, or it is escaping. So if I'll run it for more number of time steps, the bubble will fully escape this fluid domain. So in this, we can see the fluid velocity also, or the velocity of the bubble combined, how because of the bubble dynamics, how the velocity of the domain is changing. And we can do a lot of post-processing here in this, like we can visualize the vector field. So for that, I'm taking a 2D plane. So we can visualize both the streamlines and the velocity vectors also. So we'll start with the streamlines. So there is one option called as stream tracers. So if I switch it on, I will switch on the surface streamline and the velocity. So instead of taking this line, that means I have to draw the streamlines along or across this line. It will be better. So if you scroll down, there is an option called as seed. So we can define it as the point cloud. And the radius of this point cloud we can vary. And So some streamlines we will able to see. So I will give this streamlines as solid color, and the color of this streamlines we can change. So I'm not giving any field color to that streamline. So I will define in the black, I will give black color to that streamline. And how to make it dense. So you can see the option called as number of points here. So I will simply increase the number of points. Yeah. So now you can visualize the streamlines, how it is changing all over the fluid domain. So we'll start from the beginning and we'll switch off this seed sphere. So as the bubble moves, how the streamlines is changing inside the fluid domain, that you can visualize. And similar to these streamlines, we can visualize the velocity vectors also. So there is an option called as glyph. So simply click on this. And the orientation array has to be velocity, that is u, and scale array also should be u. Now you can see there are a lot of velocity vectors are coming, so that you can simply reduce from this seed option. So I will start with 1000 seed, and also I will reduce this. Yeah. And for this also I will use a single color for better visualization. And I will scale it down. Now here also you can see as the bubble moves, the vector all around the bubble, even inside the bubble, how it is changing, you can visualize. Now till here, I have shown how to set up the test case using OpenFOAM 2412. I hope using this version of OpenFOAM, everything is clear. Now, when we are using OpenFOAM 9 or .org version, there is not much difference. But I will going to explain how to set up the test case for that also. So first I will delete all the files that we have saved. And we'll exit from this environment. So 0 and system folder will be the same. Only change will be there in the constant folder, where we're going to define the properties of the fluid, of both the fluid. So in .com version, we were requiring these two files, transport and turbulence property. But in .org version, these 4 files will be required: momentum transport, phase properties, dot phase 1, phase properties dot phase 2. So we'll start with momentum transport. So it is similar to the turbulence properties file. So here also we are defining what kind of simulation we're going to prefer, whether it's a turbulent simulation or a laminar-based simulation. So in the momentum transport file, we are defining the simulation type. And then in the phase properties, we are simply defining how many phases we are defining here. So there are only two phases, phase 1 and phase 2, and what is the value of surface tension. Now the value of the properties of each phases we're going to define in physical properties phase 1 and physical properties phase 2. So the viscosity model, or what kind of fluid it is, whether it's a Newtonian or non-Newtonian, we have defined it here. And same kinematic and kinematic viscosity and density, we have defined it here for both the phases in the respective files. So this much was the difference between both .com and .org version. And for running also, I'm using OpenFOAM 11. You can use the same solver, that is Interform. And the rest all will be the same, starting from 0 to system folder. Here also we have saved some files. So this is also working. So apart from this single bubble, what if we have to see the interaction of multiple bubbles inside this fluid column? So for this, nothing we have to miss, slight changes we have to do. That too in this set field dictionary. Let me show you that how to initialize the. This is our set field option. The only thing we have to do is simply to copy this cylinder to cell, because other than this to cylinder to cell, the value we have defined for the default field is 1. That means all over the domain, the default value of the phase is 1. Now to define the multiple bubbles, we only have to define this cylinder to cell multiple times. And we're going to change this. So I'm simply, let me show you the journal. So this is the single bubble. So now if I have to define the secondary bubble or other bubble, second or third bubble. So for now, I'm simply changing the y coordinate without changing the x coordinate. You can practice it with by changing the x and y coordinate both, and by changing the radius. So I'm simply changing the y coordinate and making the bubble slightly smaller. Rest everything will be the same. Now every time when you will going to change anything, so as I've showed that we have to run the set field file, it will going to create the field inside this alpha phase. So let me show you both the files, how both files are different. So initially I have shown this alpha.phase1 original file. So in this you can see at the boundary there is no field, 0 gradient I have set, and internal field also I have kept as 0. So that's why we were not able to see any field inside the fluid domain before running the set field command. Now after running the set field command, open this. So instead of 0 field internal field uniform 0, now you will able to see that all over these 12,800 cell domain, it has written some value of alpha, starting with 0, starting with 1, and wherever we have defined the value alpha phase with a value of 0, it has written that 0 value there. So it is going to read this internal field, and based on this internal field, we are able to visualize that bubble. So it will be better if we'll delete this file and again create it without any value of internal fields. So again, I will going to run the same command, that is set fields. Yeah. Now you can see it has created 2 cells. Yeah. So the distance between both the cells were not much. It will be better if we define it apart, so that we will able to visualize both the bubbles clearly. Again, I'm running that same command. Yeah. Now we'll able. Now we can visualize both the bubbles. And after running this interform, we'll able to see the interaction or the dynamics of both the bubbles rising inside the continuous domain or continuous field. Now if I'll start to play, we can see both the bubble start to rise inside this fluid domain, and how their shapes are going to change. So this was all about multi-phase flows using VF model. So this was the case I have shown. Similar to this, where we have seen the dynamics of bubble, we can also simulate the dynamics of the droplet, where this blue region is the air or some lighter density region, and this red region is the heavier fluid, and how it will going to fall under the influence of gravity, that we can also simulate here. So this was the animation which was created. So using the same set field, we can simulate this also. So now instead of giving the default field value of 1, we can give the default field value of 0, and where we have defined the bubble with alpha value of 0, here we can define the alpha value of 1. So by doing these two changes, we can simulate the falling of the droplet also. So is there any questions?
Nikhil sir, there is a question by Mr. Sudhanshu Chaudhary. It's quite up.
Okay.
See this one, yes.
That will depend on what value of internal pressure you are giving. Sudhanshu sir, possibly if the internal pressure you are keeping very low compared to the top wall, possibly it will burst. Any other question is there, Paris?
No, sir, as of now, no.
Okay. This is a response after running the set field.
Mr. Samiullah is not able to see the bubble.
Oh, okay. So, Saimullah sir, you in the para view, there is one option called as skip zero time. If you untick it and refresh it, then apply, possibly you will able to see the field. Yeah, that is also possible with this VF model. Rajan sir. Yes, for phase change and even the boiling condensation process. So this VF model is a non-reactive solver, but for boiling and condensation, there are other solvers available in the OpenFOAM with the name. If we don't want to capture the interface, there is a solver called as reacting two-phase Euler form, where based on the saturation temperature, the flow will going to change the phase. Yes, Harish sir.
Thank you, Nikhil. So it was a very nice explanation, but I have one doubt in this problem. So if I want to make this the same that's hands-on project with the temperature stratification, so what would you suggest for this one? I had the same question with Paras also. So I was not bit clear about the approach
so
and here.
Okay. So
and the second question is if I want to make that same bubble as a rigid one. So these were my two questions. I thought I will have a discussion on this.
So rigid one. Thank you. Okay, so rigid one, as in it's some. Then you have to either go for a single phase closer, because it will, what you want to simulate, it will depend on that.
Okay.
Okay. because that kind of provision also is there in the OpenFOAM by making the mesh as dynamic mesh.
Okay.
Okay. And the second question, what you are saying that if you want to have some temperature stratification.
Yeah.
So whether you want to simulate some boiling condensation kind of problem or?
Means not boiling. It is completely like a linearly temperature stratified.
That also is possible using the same set field. So in the set field, and one more thing, this interform solver is not having any energy equation. So there are other solvers which deal with it. Okay, so that you have to use it. And again, for giving the temperature stratification, the way I've defined the alpha phase and other phases, like in the same way you can define the temperature also.
Oh, okay.
Yeah.
And we need to give the means like a small user defined.
Yes.
Function. Okay. Yeah, sure. Thank you, Nikhil.
Okay. With I've shown that while changing the bubble rising case to droplet case, only thing I've changed is this alpha value. So instead of taking the default alpha value as 1, first we need to change it to 0. And now instead of bubble, we have to define the droplet. So wherever I have defined this cylinder to cell, earlier it was having a value of 0. I have to make it as 1. Only this much change I have to do.
Hello, sir. Is audible?
Yes, sir.
Sir, usually when you do the bubble dynamics and all, usually they do the tracking of the bubble in the post-processing.
Yes.
How can you do that one in the Paravé if you want to track with respect to the time, the trajectory of the bubble dynamics?
Oh, okay. So you want to plot the trajectory of the bubble dynamics, you are saying?
Yes.
Okay. So for that, I'm not shown it here. You have to fix the probe in the. So let me show you. So suppose this is the bubble. So before starting of the simulation, you have to fix the probe here. And over the period of time, that probe will also going to move, and you can trace the trajectory of it.
But if you multiple bubbles are there, you can put multiple probes.
Yes, you can put the multiple probes. Yes.
Okay. Thank you.
No, sir, we are not incorporating the effect of contact angle. It will be depending on the surface tension. What kind of what value of surface tension you are taking. So based on that, the bubble will change its property. Even for contact angle also, I think. Let me check, sir. I will get back to you. I think some provision is there. Paris, do you know anything regarding this?
No idea, sir. About
this. Fine. You can mail us, sir. We'll check and yeah. Okay, Sudhanshu, sir. So instead of escaping the bubble, so wherever I have defined, let me show you. So in this velocity file, here instead of defining the pressure inlet outlet velocity, if I'll simply define it as fixed 0, that means no boundary condition in both velocity and pressure, it will not going to escape the domain. Okay, so Saimullah sir, if you want to create your own test case, let me show you. if you'll go inside the tutorials of OpenFOAM, so inside this OpenFOAM, if you go inside the tutorials, multi-phase. So inside multi-phase, there is these are the tutorials which belongs to multi-phase flows. If you go inside interform laminar, so these are the test cases which are used for tracking the interfaces. So you can take any one of this test case and you can change based on your application. So if no other question is there, ma'am, should I continue or we can take a break?
We can take a break. I mean, in our schedule also there was a tea break scheduled.
Okay,
So
ma'am.
we can take, I think 10 minutes was the allocated time. Let me just check.
Yes, ma'am.
Yeah, 4 to 4:15. The 15 minutes break was scheduled. So we can take a break till 4:15 and come back.
Okay. Okay, ma'am.
Thanks a lot. Hello. If you are back from the break, then we can start again.
Yes.
Should we start now, or we can wait for 1 or 2 minutes?
Yes.
I think we can start. It's 4:20.
Okay. Okay, fine. So we can start. Okay. Yeah. So I think everyone is back. So continuing with multi-phase flows simulation. So till now we have seen the multi-phase flow simulation of multi-phase flows using VOF model, volume of fluid model, in which someone is asking for the link. I think it's a
Yes,
drive
sir.
link.
Yes, sir. No, not that, not that.
Okay. Fine. So till now we have seen the VF model, volume of fluid model, in which we have seen how to track the interface of any interface of any phase. So similar to that, I want to show a few more examples, which some examples are already there in OpenFOAM tutorials. So one of it is a dam break model, in which this blue color section is the air or lighter fluid section, and this is the heavier fluid, or we can call it as a water. So under the influence of gravity, how this will going to break and flow inside the fluid domain. So as here also we are tracking the interface. So same governing equation will going to solve using the same interform model, interform solver. So this is the animation of it. So due to gravity, the heavier fluid will.
Nikhil sir, sorry to interrupt.
Oh,
Are you sharing your screen?
Oh, okay. Sorry. I have not shared it. Okay.
Yes.
I thought I have shared the screen.
No problem, sir.
Okay. Now I think it is visible.
Yes, sir.
Okay, fine. Yes. Yeah. So this is the dam break case. So this blue color section is the air section, and this is the heavier fluid section. So under the influence of gravity, how it will going to break and flow inside this fluid domain. So this tutorial is already there in the OpenFOAM. I will going to show where it is. So here also we are tracking the interface between the two phases. So again, same solver interform using the VF model is used. Same governing equations.
Hello.
Hello.
Nika?
Yeah.
Actually, you started the slide number 4, or you started slide number 1?
No, this is some examples I am simply showing. I started from slide number 4.
We are recording, na? That's why I'm asking.
Oh, okay. No, this difference, right? I have started from slide number 4 only.
Okay.
Just to show the examples. Yeah. So this is the animation of dam break. So how the heavier fluid will start to flow under the influence of gravity, and how the dynamics of the interface we can capture it from here. So as it's a very coarse mesh, so that's why the interface is not very much clear in this animation. Another is the free surface flow interaction, where a wave a wave function is given to the water, and how it will going to interact with air. That also we can simulate using interform. And this is the animation of, and this tutorial is available in our in the FOSSEE website, which you can download. I will share the link later on for this tutorial. So you can see a wave function is given to the water and how it is going to interact. That we can track using InterFOAM. So I can show where is that dam break tutorial is there. So inside OpenFOAM 2412, once you will go inside the tutorial, I think it is same for all versions. Inside this multi-phase folder, if you will go inside InterFOAM laminar. So here is the dam break folder is. I think I hope it is visible to everyone. This dam break. So it is same what I have showed here in the animation. This one. So it's the same tutorial. And this is the wave tutorial which you will practice. So these many tutorials are given. I've shown only few of it. So in the marine surf lecture, we just talked about two kinds of interaction. One is continuous fluid interaction, where we'll able to track the interface of the phases, which I've showed it in the previous hands-on session, where the bubble is how the bubble is rising, or how to track the dynamics of the bubble, or how to simulate the droplet falling under the influence of gravity. So that comes under VF model. In these cases, only a single interface will be able to capture. But when it comes to suppose in the bubble rising case, instead of one or two bubble or three bubble, there are infinite number of bubbles. Or for example, as he was talking in his lecture about fluidized bed, fixed bed, or bubble column. So inside the continuous fluid domain, what if there is a stream or a jet of air has released? So in that, we'll not able to see the each and every bubble, or it will be very difficult to track these many bubbles. So in these cases, instead of tracking the bubble, we're going to model this bubble, and we'll only able to see the effect. That okay, some sort of stream is released inside the continuous fluid, or some sort of a stream is released, or air is released inside the liquid domain. So instead of resolving the interface, we're going to model it. And these models are these models have used some empirical correlation, which are widely used in the literature. So this we're going to solve or see. So this is one of the example of fluidized bed. So where there is a bed of sand, and the air is injected from the bottom, and under the influence of injected air, how this sand bed will going to affect, and how it will going to behave. So this is the whole idea of fluidized bed. Now instead of this sand bed, what if there is a single fluid column, and the same air jet is enter inside that liquid column? So in that case also, how the whole fluid column will going to react under the influence of liquid jet. So in the this kind of modeling is called as Eilers-Fantini multi-phase flow model. So in this, both the phases, instead of capturing the interface of both the phases, will average the volume fraction of both the phase, and only effect we'll going to see that okay, some sort of void fraction we'll able to see for both the phases, and the interaction between both of them we're going to model using some source term like drag force or surface tension force. So that we're going to see. So for solving this Eilers and Eilers in the multi-phase flow model or mixture model. So earlier I have shown that for the VF model, we were solving a single continuity equation, single momentum equation, and a separate void fraction equation or alpha equation to track the interface. But when it comes to Eilers and Eilers in the multi-phase flow model, instead of solving the separate alpha equation, we'll include that void fraction or alpha in the continuity and momentum equation, and then that many equations we're going to solve. So, for example, while solving the Eilers multi-phase flow problem, air and water are the two phases. So, we're going to solve two equations for. There will be two equations, one for air, one for water, and similarly, momentum equation, one for air, other for water. So, same I've showed it here that these are two continuity equation, one for each phase, and two momentum equation, again one for each phase respectively. Now, how each phase will going to understand that okay, second phase is also there. For that, we're going to include this source term, which is called as drag term, and it will going to communicate between both the phases. And there are various drag force model. So this I'm showing it for this fluidized bed. We're going to see for the bubble column also, which I will going to demonstrate. So similar setup will be up to some height inside a computational domain, liquid will be filled, which shown with this red color, and a spray jet or a air jet will be entered from the bottom inside this liquid column, and how the liquid column will going to behave in that air stream. So this tutorial is already there inside the OpenFOAM tutorials. So if you go inside again to the same multi-phase folder, and inside this multi-phase folder, you can see this two-phase Euler form. I hope everyone will able to locate this folder. Please tell me if you are able to locate it. Inside OpenFOAM tutorial folder, but go to multi-phase folder, and in this multi-phase, two-phase Euler form. I'm showing it for OpenFOAM 2412. Later on, I will show it for other version also. Everyone able to locate that tutorial? Otherwise, okay, fine. No, not dam break, sir. It is two-phase Euler form. Dam break was for VF model. Now we are seeing the Euler and two-phase flow model. Okay, it will be better if I'll upload this tutorial in the drive, so everyone will able to download it. Please check the drive. I've uploaded the same tutorial. I will upload the zip file also. In the same folder, I have uploaded the zip file of the same tutorial. So you can download it from there as well. Yeah. Fine. I hope my screen is visible.
Yes, sir.
Yeah. So this is the bubble column. So as I said, so this will be the setup. So up to some height, this red zone is the liquid column, and the stream of jet will be injected from the bottom of this computational domain, and how the liquid column will going to behave under the effect of this jet of stream, we're going to see. So as I've said, we're not going to see any interface, only the effect we'll able to see because of Eilers-Fantini modeling of both the phases. And for that, I've shown what governing equation we're going to solve, and how the drag force modeling we are incorporating it. So if you'll see, there is one folder called 0.org. So we'll simply copy this folder and make it and rename it to 0. And we'll rename other files. If you are seeing these kind of files, these are simply temporary files generated because of Windows version. You can simply delete it. So we'll start with 0 folder. So you can see the difference in the 0 folder of both a bubble rising tutorial and this bubble column tutorial. So in the bubble rising tutorial, only 3 files were there: alpha file, velocity file, and the pressure file. Now in this, all these 3 files are there, but apart from this, it is dedicated to each phases, like U air, that means velocity of air, velocity of water, pressure will be the same, and alpha air. So why it is? Because instead of tracking the interface, we are modeling each interface, and for that we are solving the fields for we are solving each field or each phase using respective continuity and momentum equation. So other files are not required because we are solving bubble column, as it's a non-reactive and temperature will not going to affect it. So I will show only this velocity file, pressure file, and alpha here. So starting with U water. So in this also, after creation of the mesh, we'll not able to see any field because we have not yet set the field using set field dictionary. So here also we can see how the field are getting established using set field command. So as I've said, from the bottom, air will come as a stream. So that's why we are giving water as 0. So that means water will not going to drain from the bottom wall. Outlet means air will simply escape from the outlet. That means the top wall. And the other walls has given no slip boundary condition. Similar to water, if we'll see the boundary conditions for air, so from the inlet, we're going to inject the air. So that's why from the inlet fixed value, and here the internal fields. So internal fields is given as uniform. Actually better is there should not be any confusion. So inlet fixed value and value we have given. So air will going to enter from the y direction. So that's why I've defined the velocity in the y coordinate. And the value of the air velocity is 0.1 meter per second.
Nikhil, can we just take a pause because Preeti has just put in the attendance for this session.
Oh, okay, ma'am.
So I would request all the participants to please take a pause and please mark yourselves present. And Deepak, could you please put this on the YouTube also? Professor Jatinder Madan, sorry, actually, sir, we put the attendance live for each sessions of this program. So we will not repeat the attendance sheet for any of the sessions later on. So this is actually a norm that we follow at FOSSEE, that the attendance that we take are live to ensure that all the participants are present during the session, so that we somehow acknowledge them that they are going through all the sessions, and on the basis of that we award the certificates. So participants who have joined through the YouTube link, please check the chat box. Our team has put the attendance sheet over there also. Please mark yourselves present, and then we can move ahead with the demonstration session.
Nikhil sir.
Yes.
Sir, in the meantime, can you show how to access the files in the drive section?
Okay. It is inside FDP day 2 multi-phase flows, and the tutorial we are seeing right now is this bubble column.
So Mr. Indrashis sir is not able to find the folders.
Sir, can you please tell us
Yes, I'm
now
not able
whether
to
you...
see the folder bubble column inside multiphase flow.
Okay.
Okay, so if we are all done with the attendance marking, we can carry on with the session.
Sir, which version you are using OpenFOAM? I can help you in locating it.
2412.
2412, no? So you can go to tutorial, OpenFOAM tutorials. Inside OpenFOAM tutorials, so go to multiphase. Then inside multiphase, there is a folder named two-phase Euler form or two-phase Euler form. Till here, whether you are able to locate?
Where do I need to go? In 2412?
Just I'll type. Multiphase. I'm typing it in the chat box. Yes, sir, check it. So those who are not able to see this bubble column folder in the drive, they can follow this path in the OpenFOAM folder, tutorial multiphase. You will able to locate this because this is the standard tutorial in the OpenFOAM. Indrashis sir.
No, I'm still not able to locate it.
Now it's fine.
No, sir.
In the OpenFOAM also you are not able to locate this.
No, sir.
See the chat box. I have given the path. Should we move forward?
Yes, sir.
Okay, fine. Yes. So we were seeing this velocity for the air phase. So at the inlet, we are giving the air velocity as 0.1 from the y direction. Outlet same that we are allowing the air to escape. So that's the pressure we are giving. And similar to the air, similar to water, we are giving no slip boundary condition for air also on the walls. Now almost same boundary condition will be there in the pressure side also. So wherever we have defined the velocity as fixed value, that means it's a Dirichlet condition. So there we have to implement Newman condition for the pressure. So this fixed flux pressure is nothing but the zero gradient for the pressure. And at the outlet, we are defining zero pressure or atmospheric pressure, 1 into 10 power 5. Then comes to alpha air. Yeah. So at the inlet, so as we are injecting the stream of air, So that's why we have given the fixed value at the inlet. And at the outlet, simply we are allowing the phase to escape the domain. And at the wall, we have defined it as 0 drilling. So this was all about zero folder. Now coming to constant. Again, I will delete all these files. So as I said, in the multiphase, we have to incorporate the gravity term. So we're going to see all these files one by one. So here, as we are solving the continuity and momentum equation for each phase, so that means for each phase we have to define the simulation type, whether it's a laminar or it's a turbulent, because the two phases are coming into effect. So possibly one phase will be in laminar zone, other will be in turbulent. So that also we have to define. So for this case, we are defining that both the phase are in laminar, or the simulation type for both the phases are laminar. Now coming to thermophysical properties. So thermophysical properties for air and water, both we have to define. So in thermophysical properties, we have to define the transport property, which includes dynamic viscosity and Prandtl number. This anyhow will not going to affect the Cp and Cv value because we are solving it for the non-reactive or for the isothermal case. So these things will act as we can say it as dummy. So only thing will come into effect will be this two transport term, in which we are defining dynamic viscosity and Prandtl number. And in both the cases, we have to define it. Now coming to phase properties. So in phase properties, we have to define what all phases are there. And as I said, how it will going to communicate with each other. So for that, we are going to model the drag force. So that we are defining it here. And also the surface tension force we're going to define here. So for surface tension force, only surface tension value we have to give. So here is the surface tension, which is defined as sigma. And this is the drag force. So both we have to define that drag from air to water and water to air. So for that, this correlation is given because here instead of resolving the interface, we are modeling it. So some standard correlation we have to follow. And these correlations are extensively explained in the literature. If you search the name, you will get every details of this correlation. And anyhow, this heat transfer term will not going to, as this is an isothermal case, so this will not going to play any role. And other forces we are kept as dummy. So only drag force is coming into effect. So these properties will going to define it in phase properties. And anyhow, gravity will be there. So this is also a vertical channel. So gravity will act in the y direction. Coming to system folder. So system folder will be anyhow similar to the other cases. Only thing I have to show is this set field dict file, how it will going to different from the VF model. So in the VF model, for capturing the interface of the bubble rising, we defined we define the bubble in the form of cylinder to cell. So now it's simply a rectangular channel. So and as I've said, let me show you the geometry or the computational domain again. So initially half of the portion is this blue color is air, and this half of the portion is water. So this we have to tell, or we have to define inside the computational domain, that up to what height it is liquid and up to what height it is air. So initially we have defined the default value of the phase. So alpha dot air as 1. And here we are defining box to cell. So we're going to define a box in which the alpha dot air as 0. So alpha dot air as 0, that means it's water. So now we'll see how the simulation will going to progress. I'm using OpenFOAM 2412. Now again, starting with the block mesh. So as it's a simple rectangular channel, so only one block we have to define. And after that, check mesh. So even in the, if we're able to see the total number of mesh elements, it is simply 1800. So it will not going to take much time to solve. So now we'll see the mesh. So till now we haven't run that set field command. So we're not able to see any phase. Only computational domain with the mesh. So as we can see, it's a very coarse mesh. So this is the basic difference between the VF model and Eilerian flow model. So in VF model, as we are capturing the interface of any phase, so that's why the mesh should be very fine so that it can accurately capture the interface. But as in this case, we are not bothering about capturing the interface. We are modeling the phases. So we can keep the coarse mesh compared to the VF model. So now we'll go move forward with set field command. So here also alpha dot air phase is there. So we have defined the default value of 1, and we have defined the box with the alpha dot air value of 0. So alpha dot air value of 0 means some sort of liquid is present there. Now if I'll so now alpha air is also visible. Yeah. So this alpha air 0 means in this blue portion some sort of liquid is there, and here it is air. So this we have set up the initial test case. Now instead of using the interform as a solver, we'll use two-phase Euler form or two-phase Euler form as a solver. And this solver will consist of all the equations which I've showed earlier in the slides. So as this is a very coarse mesh, it will not take much time to complete the simulation. And you can check the control rig, what is the end time. So it's 100 seconds, and write interval is 1. That means after every 1 second, it will going to save one file. So that also we can check that after every 1 second, it is saving one file. So let it run at least till 10 seconds.
Hello, Nikhil sir.
Yeah.
The screen has frozen.
Oh, okay. Now?
No, sir.
Okay.
Still it is like that.
Now can you tell me whether the folders are visible?
No, sir.
No?
I'm just
Okay.
able to see the terminal.
Okay, okay. Let me stop the presentation and then.
Sure.
Now is it visible?
Yes, sir. Yes.
Okay, fine. Even the terminal also.
Yes, sir.
Okay, fine. Thank you. Okay, so we'll stop. It has run till 12 seconds. Now paragraph is visible, right?
Yes, sir.
Oh. So these many files we have. So we can see. So this is the inlet section. So from here we are injecting the stream of air, and this is the outlet. So we are allowing the air to escape the computational domain. And this blue color is nothing but our water column, and how it will going to behave under the influence of air jet. So we can see that it's a stream of air. So that's why instead of capturing the bubbles of air, because a lot of bubbles will going to be injected from this inlet. So it will be completely very expensive to track each and every bubble. So that's why we have modeled it. And this is how it is going to look like. So it will be a transient simulation. And we'll only able to see the effect, that how both the pairs are interacting with each other. So this kind of simulation will be further useful when we are solving for boiling or condensation problem, where a lot of bubble are forming over the heated surface. So instead of resolving each and every bubble formed over the heated surface, we'll use such kind of Eulerian flow modeling to get effect. Okay, some sort of phase change is there over the heated surface, or even in the case of fluidized bed, which I've showed. So there also bed of sand is there. So instead of resolving the each and every particle, it's better to model the sand bed and also the air injected or some sort of fluid injected inside that bed. And this was all about multi-phase flows. Now further, to see the post-processing, you can plot the streamlines and velocity vectors. And for the today's session, we have taken the non-reactive kind of multi-phase flows. For reacting kind of multi-phase flows, I can show some tutorials where you can simulate boiling problems also. So if you go inside the OpenFOAM tutorial folder, inside tutorial multi-phase. So now if you're able to locate this reacting two-phase Euler form or reacting multi-phase Euler form, any one of it, go to laminar. Yes. If we go to RAS, that is it's a RANS modeling. So this wall boiling. So this wall boiling simulation will consist of boiling over the wall or flow boiling kind of simulation. So this you can explore. And even the flash bed simulation is also there. So this you can explore easily now. So this was all about multi-phase flows using VF model and island two-phase flow model. So if any question is there,
Nikhil sir, can you take the question by Mr. Samiullah?
yeah, this one. As you can see, which command has been. Oh, okay. So it is. I will type it here, sir. The solver name two-phase your form. This was the command I have typed after the set fields. Then it's always good for a particular type of problem. Ankit sir, it depends on what kind of problem you are referring to. So suppose if you want to capture the bubble interface or some sort of interface, interform or interisoform solver will be better. But if you want to see the effect of one fluid on another, or simply a modeling like what we have seen in the bubble column problem, then two-phase Euler form or Euler modeling solver will be good for it.
Does anyone has any questions to Nikhil sir? They can ask. They can unmute themselves, or maybe they can put it in the chat box as well. If there are no questions, then maybe we can call
We
it
can
off.
end the session.
Okay.
Can cavitation also be modeled? Yes, sir. It is possible to model the cavitation, and even the if you go to tutorial section of OpenFOAM, one cavitation problem is also there. You can explore it. Jitendra sir, what kind of medical related simulation you are referring? You can unmute it and for microfluidics is possible to do. Yes, heart, even arteries, blood flow kind of simulation, you can do it in OpenFOAM. Mayank sir, I'm not familiar with this kind of problem. We'll look into it, and if we'll get something, we'll share it with you.
Hello.
Yes, sir.
Paris J. I want to talk with you.
Okay, yes.
Can we have tomorrow more hands-on on post-processing, or because what happened today, we learn lots of things, but due to the Windows upgradation from my system 10 to 11, previously I installed that OpenFOAM, but it is not locating the files where it should be. So problem is that arriving. So I'm taking the help of ChatGPT to run this course, and it is working. But only the problem is coming me for the post-processing or data extraction or data visualization. So I'm expecting that if we get that much of hands-on remaining 2 days, it would be helpful a lot.
Yeah. So Ganesh sir, we have a dedicated session planned on day 4, second half, on post processing only. So we are going to do only post processing using Paraview. So one session is dedicatedly prepared for post processing. Tomorrow we have passive scalar for chemical engineers and a case study session on heat transfer.
Oh, good case studies for heat transfer. Nice. Thank you, sir. Sir, and I also want to do we have in future again better meshing related this?
Yes. So,
because
sir, due to time constraint, we have to skip it out. But we conduct workshops every second month. So you can expect a session in the month of August.
So in the August we have the meshing only to related meshing.
Not related to meshing completely, but one part of it will be dedicated for meshing.
Yeah, because what happened? I just want to tell you, when we go for industry, I saw many friends. They are have hands-on very good in ANSA or hypermesh. So if we have that much of exposure here, na, our 80% problem will get solved, because industry wants. While my interaction with him, he told me that industry wants 80% problem solved by your meshing is done properly.
Yes.
So if we go for heavily on meshing, it will really help us to extract our horizons in this field. So that's what I'm expecting. If you could align such a meshing related 1 week training sessions, it would be really good for industry point of view.
Sure,
Industry
sir.
as well as this academics also.
Okay, sir. Noted. Hopefully,
Because I'm going to join L&T coming weeks. So I was thinking that if meshing would be, then it could be good.
Sure, sir. Sure.
And after joining the L&T, will it be possible me to join these sessions?
Yes, sir. You can join this session. Only thing is, whenever Payal ma'am floats the advertisement, you have to fill the form.
Okay.
So if you have filled the form, there is no issue.
Okay, because here this time they told that faculty. That's why I'm asking you.
Yes. No problem, sir. You can join it. No problem.
Okay. Thank you.
Thank you, sir, for the suggestion as well.
Yes.
Any
Am I
more
audible?
sir? Welcome as well. Yes, Vinod, sir.
Yeah. So I just have a kind request to you. I mean, yesterday's session was really so interactive, and hands-on were also comfortable. But I mean, for me personally, I don't know about others. Today I faced a lot of challenges while following the speaker. In terms of hands-on, I'm specifically saying. So that would be so nice if you could pay some attention towards hands-on. because in
Okay.
first half today, the session organized by Fernandez, so that was too fast. And
Okay,
I mean, as
okay.
a whole today, I really was
Hmm.
unable to follow the hands-on sessions compared to
Okay.
the yesterday's session. Today was little hectic. So can you kindly, if
Hmm.
you could focus on hands-on, so that would
Okay.
fulfill our purpose of attending, day-long sessions
Yes,
and
yes.
getting
Understood, sir.
something end of the
Understood.
day.
Yes, sir.
Yeah.
Yes, sir.
So
Understood.
thank you.
Yes, yes. We'll make sure that, sir, it happens like, if the session is bit delayed, we have to cover a lot of things within the certain amount of time. That's why we have to skip it. That is the reason if you might not be able to get what Ivan sir did in the session in the morning. But okay, no worries. I have taken your suggestion. Um we'll make sure, so instead of keeping two case studies, we'll keep one case study only so that everyone can follow along with this. Okay, sir.
Yeah, exactly. I mean, it's my personal opinion that instead of focusing on quantity, if we could focus on quality, so that would be much better to follow and practice on ourselves also.
Hmm.
If we fundamentals are clear.
Okay, okay, sir. Yes, understood. Yes, noted, sir.
Thank you. Thank
Thank
you
you.
so much. Yeah, thank you.
Yes, thank you so much, sir. Kalyan sir, I'm not sure about this. uh, Maybe we have to we are planning for a community program development, but it is in the preliminary stage, so I cannot uh, say anything regarding this. On FSI, Dr. Mr. Irshad Alam sir, what you can do is, see, Dr. Chandan Bose sir, who gave the talk yesterday, so he does both IBM as well and this as well, fluid structure interaction as well. So on our website, now you can check out. There are some case studies available on FSI, and for IBM, I don't think there are any tutorials available. The the FOSSEE team is working for publishing some work in IBM part as well. We have comparisons of ALE mesh versus IBM, but not a dedicated tutorial. And we also know that installing foam extent for immerse boundary methods is quite challenging. So we are preparing a documentation part. It's almost done. So hopefully, maybe in 2 weeks, we'll be floating the installation for Foam Extend 5.0 for immerse boundary methods, and hopefully you can expect some tutorials from that point as well. Any more questions or suggestion?
Uh, Paras, one thing just I want to know.
Yes, Vinod sir.
Yeah. So, I mean, after this sessions also, I mean, after completion of this training program, so
Mm-hmm.
can we come back to the volunteers or organizers like you and others whenever we face some issues? Because see, I mean, we're just 2 days old with the with the open form and all.
Open
I mean,
forum.
personally for
Mm-hmm.
me, yeah.
Yes. Yes.
So in that case, definitely we will face a lot of issues. And as you know that open form is little tricky compared to other
Mm-hmm. Yes.
commercial softwares because of
Mm-hmm.
the very limited community. So
Yes,
will you
sir.
be available and
Yes, sir. We are
will
24.
we get
Me, Ivan, sir. Yes, yes.
yeah, please go ahead.
Sir, me and Ivan sir are full time here at ITB, so we are available full time. You can email us on contact-CFD. One of us will respond to your query 100%. In
Yeah,
future
that
as
would
well.
be so great and helpful. Yeah.
Sure, sir. Sure, sure. If you need, yes, Payal ma'am has given our email. So if you just email us on here, na. So if you have any query related to Chandan sir or any of our faculty members, using this email only, we can forward your query to the respective person. And also, yes, I understand the website is not working. The website is down. The web team is migrating some part of it. hence the URL is not working, but we are optimistic that it should be working by the end of this workshop, so that we can show you a glimpse of our website as well, and we can show you how you can download a case study. And because we make sure that if anyone who is new to OpenFOAM should be also able to understand what is given in the case study. So we make our case studies in that manner. So if you install any case studies from our website, we have given everything from scratch in the report, so you have to follow the report. All run cases are also available. So once our website is live, I'll definitely give you a demo of it. Also, Payal ma'am will also show you how to navigate to our website, but particularly for demo part, we are there. I hope it addresses Mr. Vinod sir.
Yes, yes, definitely. I mean, that would be great to hear. Thank you so much.
Thank you, sir. Any other suggestion? Mr. Jatindan sir, are you?
Yeah. So could you please share your email ID?
Okay, my personal email ID.
Yeah, whatever means official or.
Okay, so one is this contact CFD.
Okay.
This one is for the FOSSEE team,
I
and
think contact CFD will be better, sir, because all our team members access this website, and whoever is free or whoever is viewing your query, first of all, they'll actually be able to address it. So it's better if you write at contact-cfd@fossee.in. I've just typed it in the chat box.
Okay. Thank you.
Any
Hello,
other
sir.
questions? Yes.
Sir, this is a basic level we're doing in FDP. Is it any possibility in future we can have the application oriented,
Yes, sir. So the thing is, we have at least 3 to 4 workshops in throughout the year. So we start from a basic workshop, then we go to intermediate level workshop, and then we go to advanced level workshop. So for advanced level workshop, this year it was conducted at IIT Bombay only offline. So people were there from, some people joined online, some people were there from Bombay as well. So yes, we do them, but for advanced level or intermediate level, we get people from the specialized domain only. So let us say if someone is asking about immerse boundary method or fluid structure interaction, dynamic meshing, so we deal with them at that point only. For regular workshops, it's quite difficult, as catering to every audience or every people in the there are people joined on YouTube as well. So considering them, we have planned this session. But definitely, if you have any suggestions for this, you can let us know. We'll work on it.
But can we associate with FOSSEE team? Can we organize the FDP in our college like that? In some paid FDP sort of things, like local people can be connected.
Yes, so we can do. We
Payal
can do.
ma'am can answer
We
this.
can do. So for your specific topics, only for your specific institute, we will be able to arrange a online training session. Sir, may I please ask you, where are you located, sir?
Bangalore, ma'am.
Bangalore.
Yes, ma'am.
Okay,
Because
in
in
that
our
case,
colleges, we
we
have
can
some.
also, our team members can also visit your college and take the hands-on session, and for the intermediate level workshop.
ma'am.
So in that case, I would request you can also invite other institutes who are nearby your area, so that we can, we actually always try to reach out to a maximum number of audience, so that we can train them and upgrade them. So in
Because,
Bangalore, we'll be happy to visit your college, and if you organize the training program. It will not be on a payment basis, because this project is funded by Ministry of Education, Government of India. So we at present we are not accepting any payment, but only the commuting expenses and staying and food and lodging thing.
yes,
That
ma'am.
will be
Because
accepted from the
in
institute.
our colleges, we have funding for the FDP program.
Mm-hmm.
With that, we can take care of that for
We can do that.
accommodations.
So if you can fund our travel and stay and food, we will be happy to visit your college and do this program.
Yes, ma'am. So I'll be in contact with you.
So after this activity, we can take it forward.
Yes, ma'am. Thank you.
You can write to us at contact CFD. Then I'll directly write to you from my own email ID.
Okay. Thank you.
Thank you.
Yes, Mr. Vednath ji, do you have any doubts?
could you please mute yourselves and listen to all the participants?
Versions of OpenFOAM. I installed OpenFOAM version 12. The demo was in 2512, 2412. Someone also worked in OF9. I just wanted to know. If somebody would suggest, and what is the main difference between these different versions, like 2412 and 12?
Okay. So, sir, see, previously it used to come under a single tree. Now it has branched out. So, one company it is governed by the ESI group, and one company it is governed by the foundation group. So, in the ESI version, we generally get OpenFOAM versions like 2412, 2506, 2512. Now, maybe in the coming week, maybe 1 or 2 weeks, we will get 2606. So the updates are quite regular in 2506 or the ESI version, I would say, and the updates are quite bit irregular in foundation version. And also the ESI version, people are taking up the overset mesh cases, very as a importance. So we are getting a lot of updates for overset part in the ESI.
Okay, if I have to start working in OpenFOAM, which version should I install?
Sir, it depends on the preference. So I personally started with OpenFOAM 2312 back in 2024. But I have seen people using the foundation version like OpenFOAM 9. They feel like the learning curve is easy there.
Okay.
Yes. I hope this addresses your
Okay,
question.
thank you.
Yes, thank you.
Yes, thank you.
Yes, Mr. Pratik.
Hello, sir.
Yes.
Sir, I would like to ask, are there any internship opportunities available in IIT Bombay, as in remote it's available?
So, yes, Mr. Pratik. So,
Because I'm not unable to open the FOSSEE website. I don't know if that's a problem on my end. So
No, actually,
So-
FOSSEE website is down. So yes, we have internship opportunities year long. The first one has already been completed. It started in the month of January. So for the first 3 months of the, I mean, it was for a complete semester. Then at present we are doing this fellowship program, summer fellowship, and again in the month of August, September we will announce the autumn internship. So so we have these programs throughout the year, and apart from that, all of you are requested to please go through all the OpenFOAM tutorials. Once our website is up, I'll show you how to refer the resources and expedite your learning of OpenFOAM. And then all of you are requested to please try to submit a case study. Once you complete once you use OpenFOAM to complete a project and submit it and publish it, you will gain that confidence, and then all the students can apply for the internships and fellowships. And apart from the internships and fellowships, this case study publication and research migration publications are open. All these two projects are open throughout the year. So I'll talk in elaborate towards the conclusion of this FDP on 5th of June, that we have one program for exclusively for the faculty members. We call it the lab migration project. Students are also invited to contribute in that, and we have this case study and research migration projects for all, open for all throughout the year. So these things I'll talk to you all in detail towards the end of the session.
Okay, ma'am.
Yeah.
Okay. Thank you for actually taking time to present the whole documentation and how the learning goes for OpenFOAM. Thank you, sir.
Thank you, Mr. Pratik. Any other query or suggestions? If not, then maybe we can call it off for the day.
Yeah, we can wind up the session for today.
Okay.
Thank you everybody for joining. And if you have any questions after this session, please feel free to write to us through contact CFD. Okay, we will be answering it. So tomorrow morning, we will start the session with Professor Dheeraj Garg's talk. Professor Dheeraj Garg is from Shiv Nadar University, Noida campus. And in the second half, we will have Professor Manimaran from VIT Chennai. So tomorrow's sessions will also be very informative and full of learning opportunities. So we take your permission and leave this meeting for today. I really look forward to meet you again tomorrow. So please make sure that you log in a little bit early like you did today. So that was all for today. Thank you and bye-bye.
Thank you, everyone. Have a good
Thank
day.
you. Thank you very much.